Yeah, hi everyone, welcome to PrepFusion. So in the last video, we studied about depletion and enhancement type of MOSFET, right? Now we need to study these topics. First, we will study about MOSFET circuit symbol. Then some questions we will see like what is the use of oxide, why do we bias the MOSFET in enhancement mode for amplification. So these kind of questions we will see, theoretical questions, okay? And then we will study about channel and modulation. This is very important, very important, okay? We will study about channel and modulation, and then we will solve some questions, some numerical problems we will solve, and after that we will study the concept of biasing and transconductance. So these topics we need to study. Now all these topics I have already taught in analog electronics. Now there would be some people who have already studied analog electronics from me, so you guys don't need to watch this particular video. You can simply revise your analog notes, or you can simply revise through this video as well. If you have already studied analog electronics from me, then you don't need to watch it. Now there would be some guys who have just taken the EDC course. Okay, if you are someone who have just taken the EDC course, then you need to follow this particular video. So we are going to study these particular topics which are very important from the perspective of EDC as well, from the perspective of analog as well. Look, what happens is that when they ask these kind of questions, they ask from the perspective of analog electronics. But I have seen the PYQ books. In PYQ books, there has been some questions from these particular topics. So if I don't deal these topics in EDC, then you might feel like that, sir, we are missing out of something, right? So you are not actually missing out of anything. What I am going to do is that I am going to upload all the concepts which are required in EDC from the lectures of analog electronics. So I will simply add up the videos of analog electronics and then you will watch these content. Okay, so everything will be discussed in this particular video. So let's get started. Hi everyone, so let's see the MOSFET circuit symbol now. So what do you mean by circuit symbol? Like we have studied diode. So diode was, in physics we studied like this. This was our diode, but in the circuit analysis we were using it like this. Similarly, we have studied MOSFET like this. This is our MOSFET, but in the circuit analysis we will use it differently. So how we will use it? Like this. So first let's see about depletion type of MOSFET. So this is our depletion type of MOSFET. So these are for NMOS. These all are for NMOS. Depletion, enhancement, and common for both, like for depletion as well and for enhancement as well. And these are for PMOS, P channel. These are for P channel. These are for PMOS. So how do you denote it for depletion type? There are two solid lines. These are the solid lines. This is the solid line, and then this kind of structure. Now this potential will be drain, this potential will be source, and this potential will be body. Now there will be a sign of arrow. So how that arrow will look like? So when we study N channel, this is the P substrate and then there is N plus, right? This is our N channel MOSFET, right? P substrate and N plus. So how does the diode look like? Diode looks like this. So the arrow of diode is from, this is our body and this is our other terminal, you can say source or anything. So from body to, this is the arrow, no? Diode, arrow of diode, it is getting outward from body. So this will be the direction. And in case of PMOS, this will be the direction. This will be body, this will be source, and this will be drain. Drain. Here it is shown that source and body are shorted. Here it is shown that source and body are shorted, because in both PMOS and NMOS we are keeping source and body shorted. So here it is shown source and body are shorted. You can actually make it like this as well, like it is not shorted. In that manner also you can make, but generally we make source and body are shorted. So generally you will find it like that. So drain, source, gate, body, like that. What will be the arrow direction? How do we define the arrow? The arrow is, you will, in the mind you will think, okay, my body is, my substrate is, this is my body, my substrate was P type, and channel was N type, so from P to N, this will be the diode. So arrow will be from body to inside, getting out of body. So that will be the direction of arrow. So this is how you make the arrow. And in case of PMOS, it will be opposite, because here the substrate was N. If the substrate was N, this would be the direction of arrow. So the arrow is getting into the body, the arrow is getting into the body. Well and good. Again, here similar structure is there. This will be drain, this will be source, this will be body. What will be the arrow? Same direction, inside. Here outside. This will be source, this will be drain, and this will be body. But the lines are dashed. Here dashed line is used, this is dashed, and here solid line is used. What is the reason? Solid line shows that the channel is already present, and dashed line shows that the channel is not there, you have to make the channel. Solid line shows that the channel is already present. So in depletion type of MOSFET, channel was already present. In enhancement type, we made the channel by applying gate potential. So that's why dashed line is used in enhancement type and solid line is used in depletion type. Got the point? Now, by this arrow, you will recognize whether it is NMOS or PMOS. If arrow is inward, that means it is NMOS. But arrow from body terminal, here the arrow will change. That we will talk about. So arrow from body terminal, if the arrow from body terminal is inward, that means it is what? NMOS. If the arrow is outward, it is PMOS. Now, how will you define the source and drain? It's not that the upper one will be source and lower one will be drain, and here upper one will be drain, lower one will be source. Nah. Generally, it is shown like this. But this is not the case always. So the one which is at higher potential will be drain, and one which is at lower potential will be source in case of NMOS. I told you, remember the last lecture. In NMOS, which one is at higher potential? In NMOS, you apply positive bias at drain. So in NMOS, which one is at higher potential? Drain is at higher potential. So one which is at higher potential, in case of NMOS, that will be drain, and lower potential will be source. So if any particular circuitry is given, any particular MOS is given, they haven't shown drain and source, you don't know that, but you know the absolute potential of two nodes. You know the potential of this node is 6 volt, you know the potential of this node is 4 volt. So first you will see the arrow is inward, from body arrow is inward, that means it is NMOS, and if it is NMOS, that means higher potential will be drain and lower potential will be source. So wherever you see high potential, that will be drain, and wherever you see lower potential, that will be source. Well and good. And in case of PMOS, what will happen? The source is at higher potential, because in case of PMOS, what do? We apply negative potential at drain. Negative potential at gate. So source is at higher potential. So here I will write higher potential. I will just write HP, higher potential. And here I am writing lower potential. This is higher potential and this is lower potential. So I am also writing the shortcut, higher potential. And what do you mean by LP? Lower potential. And generally it is shown like in case of NMOS, we show drain upward and source downward. Why drain upward? Because drain is at higher potential. Always higher potential is shown upward and lower potential is shown downward. Like let's assume you make this kind of structure, no? Sometimes this is ground, this is resistance R, this is 5 volt battery. So higher potential is always upward, lower potential is always downward. You won't see circuits like this. Like you can make it like this, but generally it is shown like this: 5 volt resistance and then ground. So 5 volt device and ground. So higher potential is upward, lower potential is downward. Here what is higher potential? Higher potential is source and lower potential is drain. So higher potential upward. So generally it is shown like this, but by the direction of arrow you will get to know. If from the body arrow is outward, that means that is NMOS. If the from body the arrow is inward in the body, that means that will be PMOS. Now here, if the arrow is outward, that will be what? NMOS, and if the arrow is inward, that will be PMOS. And the one which is at higher potential, that will be drain, and one which is at lower potential, that will be source. Here this will be source, this will be drain. Although this shows the direction of arrow, although this shows the direction of current, this arrow shows the direction of current. In case of NMOS, what is the direction of current? Remember it. In case of NMOS, what is the direction of current? Electrons travel from source to drain. That means direction of current is from drain to source. So this is the direction of current in case of NMOS. So this is the most general circuit. In 99.95% cases, this will be used. You will see this kind of circuit in 99.95% cases. And here, this is the higher potential, this will be the lower potential. If you know the absolute potential of drain and source, then you can make drain and source by your own. If you don't know the absolute potential, let's assume there is some circuitry given like this. There is some circuitry given like this, and some resistance R is there, some 5 volt is there. This is some resistance R, this is some V. Do you know the potential of drain here? No. Do you know the potential of this node? I'm not saying this is drain. Do you know the potential of this node here? No, you don't know. And this node is grounded. Let's assume this is also resistance R. Do you know the potential of this node? No. So by default, you will consider this as drain and this as source. And you will consider the direction of current like this, from drain to source. But if you know the absolute potential, like let's assume this structure is given. Whatever it is, it can be anything. Let's assume this is 6 volt and this is 4 volt. So you know the absolute potential now, that this is 6 volt. That means first what you will see the arrow. Arrow is outward. That means it is certainly NMOS. It is NMOS. So it is NMOS. Now the one which is at higher potential, that will be drain, and this will be source. Well and good. And here the one which is at higher potential, that will be source, and one which is at lower potential, that will be drain. And what is the direction of current in case of PMOS? Holes travel from source to drain. So the direction of current will also be from source to drain. So this is the direction of current. And this is higher potential. This is lower potential. Actually, most of the time when we study, people say that, okay, this is NMOS, just remember it. And this is PMOS, just remember it. But this is not the case. This is NMOS, this is PMOS, that's for sure. But you can't say that always this will be drain and always this will be source. No. The structure of MOS is symmetrical. Drain and source can be interchanged based on their potentials. Understood this point? Based on their potential, the source and drain can be interchanged. And this is general kind of structure. This will be based on, let's assume this is higher potential and this is lower potential. This is how I am making. So this is our NMOS. Here there is no arrow, nothing. Just the difference is there is this bubble there. This bubble is there. This small bubble is there. In case of PMOS, this small bubble is there. So this will be source, this will be drain. This is at higher potential, this is at lower potential. Well and good. Understood this concept? So these are the symbols. These are the most important one. These are used in digital circuitry. In analog, this symbol will be used. Somewhere you can see this symbol as well, but most generally this symbol will be used. So like that, arrow is outward, that means that is NMOS. Arrow is inward, that means that is PMOS. But also the higher potential will be source and lower potential will be drain in case of PMOS, and higher potential will be drain and lower potential will be source in case of NMOS. Let's see a question and that will clear your concept now. You have to mark source, drain and the current direction. This is what you need to mark. Which one is source, which one is drain, and what will be the direction of current. So what you will do, this particular structure is given. You see this is the arrow. That means this is NMOS. First thing I got to know is that this is NMOS. Now I know one thing. What is that? That in case of NMOS, the one which is at higher potential, that is drain. So this will be drain and this will be source. And what will be the direction in case of NMOS? What is the direction of current in case of NMOS? The direction of current in case of NMOS is drain to source. So this will be the direction of current. That is ID. If you see this structure, you will see that arrow is inward. That means this is PMOS. This is PMOS. Now in PMOS, I know one thing. What is that? The one which is at higher potential, that is source. The one which is at higher potential, that is source. That means this will be source and this will be drain. What is the other thing do I know? The other thing I know is that in case of PMOS, the current always flows from source to drain. Current always flows from source to drain. So this will be the direction of ID. Let's see this. I see this structure. What do I get to know? That this is an NMOS. Just as I see this structure, I get to know that this is an NMOS because the arrow is outward. One thing I know that in case of NMOS, the one which is at higher potential, that will be drain. So now this will be the drain. and this will be source. And what is the direction of current? From drain to source. So this will be the direction of current. Now a lot of people will say, like I'm saying 99% of GATE aspirants who haven't studied analog electronics deeply, if this question is given in front of them and I say that my gate potential is 5 volt, and if I ask them what is the operating condition of a MOSFET, whether it is on or off, so what they will say? They will say that, sir, 5 minus 6, your VGS is minus 1 volt. That means VGS is less than 0, so diode is off. This is what they will say. But this is not VGS, this is drain. Because mostly what is taught is that wherever you see this arrow, that means this is source. This is wrong. Arrow doesn't mean this is source. If the arrow is outward, that means this is NMOS. That's it. Nothing else. If arrow is outward, that means it is NMOS. Nothing else. Understood the point? But when you study amplifiers, you just get habitual that this will be source only, this will be drain only, because amplifier are biased in a way that always higher potential will be upward only and lower potential will be downward only. They are biased in that way. Like with the supply, we make sure that the upper potential is drain and lower potential is source by the supply only. So in case of amplifier, you can say that, okay, sir, this will be drain, this will be source. But here I am talking about DC biasing. DC biasing. I have fixed my potential. The upper one is 4 volt, the lower one is 6 volt. That means the one which is having higher potential. Now the arrow doesn't define the direction of current. What arrow is saying? Arrow is saying that direction should be like this. This is what arrow is saying. But actually the direction is from drain to source, from down to up. Are you getting this point? And 6 volt, one which is higher potential, that is drain, and one which is lower potential, that is source. Now I see this arrow, the arrow is inward. So first thing that I got to know is that this is PMOS. This is the first thing I got to know. This is PMOS. Now if this is PMOS, what do I know? That one which is at higher potential, that is source. In case of PMOS, one which is at higher potential, that is source. So which one is higher potential? This is the higher potential. So that is source. And one which is at lower potential, that will be drain. So this will be drain. What will be the direction of current? This will be the direction of current from source to drain. Are you understanding this point? So this was a very important concept which usually aspirants ignore, but now you understood it. Okay. But in case of amplifier, you will not have to think that much that, okay, sir, which will be drain, which will be source, because they will be biased in a way that this will be drain only, this will be source only. And in case of PMOS, this will be source only and this will be drain only in the amplifiers. But here I am talking about DC biasing. In DC biasing, I can interchange anytime. Let's move on to the next concept. Before moving on to the next concept, we will solve a simple problem. So it is given that mu p, that means mobility of holes, is 0.4 times of mobility of electrons. I don't need to write it in statement, right? You will understand. The mobility of holes is 0.4 times of mobility of electrons. What must be relative width of n channel and p channel devices of relative width of n channel and p channel devices, that means NMOS and PMOS, if they are to have, that means if they are having equal drain currents when operated in saturation mode with on drive voltage of the same magnitude. What is on drive voltage? Overdrive voltage, sorry, not on drive, sorry. Overdrive. What is overdrive voltage? Overdrive voltage. Overdrive voltage means VOV, we should show it, and that is VGS minus VT only. Basically, I told no that VGS is greater than VGS minus VT. If VDS is greater than VGS minus VT, it will be in saturation region. So this potential is known as V overdrive. V overdrive is VGS minus VT only. Okay. So this term I forgot to introduce you. So V overdrive is VGS minus VT. Always remember it. Arey wah. V overdrive is VGS minus VT. This is V overdrive. Both are operating in saturation mode. Both are operating in saturation mode. And they are having equal drain currents. The current is equal. So the current of PMOS is equals to current of NMOS. So what is the formula? For PMOS it will be mu P COX W by 2L. Both are in saturation mode. So that's why I am applying P by 2L. Yeah. This V overdrive is VGS minus VT. Also it can be. This is for NMOS. And what it will be for PMOS? For PMOS, if we know one thing, for NMOS, if we know one thing, what we can do? We just need to interchange. VGS will be interchanged by VSG, and VT will be replaced by mode of VTP. So this is for PMOS. Here I can write VTN. This is for PMOS. Now mu n CoX W by 2L VGS minus VT. VT. Okay, sorry. This is we are writing for PMOS. So we will write VSG minus VTP whole square. And what we will write for NMOS? Mu n CoX W by L. Relative widths if they are having equal drain current when operated in such a manner with the same magnitude of this, and even this CoX is equal. This is what should be written, that this oxide capacitance is also equal. Oxide capacitance you will consider equal because there is no information given about it, so we are considering it equal only. So here what will be the relation? Mu n CoX W by 2L VGS minus VTN square. Now what is this? VOV. And what is this? VOV only. Both are equal, but here W by L is not equal because they are asking, what they are asking, the relation between the width of N channel and P channel. So this W by L is not equal, so I should write W by L for PMOS. So mu n CoX W by L for PMOS divided by 2. This will be the formula. Mu n CoX W by L by 2 VSG minus VTB whole square. And here what will be the formula? Here the formula will be mu n CoX W by L N by 2. Right? This CoX and CoX can be cancelled. This 2 and 2 can be cancelled. And overdrive voltage are same with the overdrive voltage of same magnitude. That means this complete term is same. So what you are left with? You are left with mu P W by L P is equals to mu N W by L N. So we have to find that mu P is equals to 0.4 mu N. Mu P is equals to 0.4 mu N. Right? 0.4 mu N. So basically this mu N and mu N will get cancelled. So this I can replace with 0.4. What did I do? In case of mu P, I put 0.4 mu N. So mu N to mu N got cancelled and only 0.4 is left here. So what will be the relation between W by L of P should be 1 by 0.4. 1 by 0.4 is 2.5. Should be 2.5 of W by L of N. So if the mobility of holes are 0.4 times of mobility of electrons, then to have the same current, the width of PMOS should be 2.5 times of width of NMOS. Did you understand this point? Mobility is lower. For PMOS, mobility is lower. So to have the same current, you have to increase the width. Understood? Mobility is lower. So to have the same current, width should be increased. Right? So width should be 2.5 times of N. Very easy question. Let's move on to the next one. For an N channel MOSFET, if the conduction parameter, look, this Kn is written there. Now, what is Kn, this conduction parameter? So sometimes Kn can be mu n CoX W by L, and sometimes this Kn can be mu n CoX W by 2L. In the examination, certainly it will be written in bracket it will be written that Kn is mu n CoX W by L or 2L, whatever they mean. If they mean W by L, they will write it. If they mean W by 2L, they will also write it. Okay. So in the examination, it will be written. So here also it is written. This is given. This is given. Given in the question. It will be given in the question that Kn means mu n CoX W by L or mu n CoX W by 2L. तो कौन सा भी हो सकता है, वो डिपेंड करेगा एग्जामिनेशन में, एग्जामिनर क्या चाहता है. So it would be given, sometimes they take mu n CoX W by 2L, sometimes they take mu n CoX W by L. So it will be given for this question, Kn is mu n CoX W by 2L, right? Now what is given? So value of mu n CoX W by 2L is given. That is 0.249 milliampere volt square. The value of VGS is given, that is 2 VT. The value of VT is given as 0.75 volt. So basically this will be 1.5 volt. The value of VDS is given as 0.4 volt. You have to find the drain current. So what will be your first step? You have to find the drain current. What will be the first step? The first step will be to determine the region of operation, whether it is in saturation or it is in linear. So how will you determine it? Whether it is in saturation or linear? You will determine with the value of VDS, VGS and VT. So what is V overdrive? V overdrive is VGS minus VT, and that is equals to 0.75 volt here. What is the value of VDS? VDS is 0.4 volt, right? VDS is 0.4 volt. So here what do you see? That your VDS is lesser than V overdrive, or you can say your VDS is lesser than VGS minus VT. That means it is in linear region. So your MOS is working in linear region. Did you understand this? What did you do? We have VGS value, VT value and VDS value. So we determined the V overdrive voltage. V overdrive voltage was VGS minus VT, that is 0.75. Then we saw VDS value. VDS value is 0.4 only. If VDS is 0.4, so it shows that VDS is lesser than VGS minus VT. So VDS is lesser than VGS minus VT. VDS is lesser than VGS minus VT. That means it is working in what? It is working in linear region. MOS is working in linear region. What is the current in linear region? The current in linear region would be mu n CoX W by L VGS minus VT into VDS minus VDS square by 2. So what is the value of mu n CoX W by L? Value of mu n CoX W by L will be 2 times of 0.249. 2 into 0.249. What is the value of VGS minus VT? VGS minus VT is 0.75. What is the value of VDS? That is 0.4, right? It is 0.4 minus 0.4 square by 2. So you just need to solve it and you will get the value of IT. Okay, let me solve it and I will write down the final answer. Yeah, so you are getting 0.109. So tell me, it will be ampere or milliampere? Milliampere. Why so? Because this is milliampere by volt square and this complete unit is volt square only. This complete unit will be volt square only because this is voltage square, this is also voltage square. So this complete unit will be volt square. So volt square to volt square got cancelled, milliampere is left. The current will be milliampere. ID is 0.109 milliampere. Well and good. Okay. Let's move on to the next concept. It's not concept, there will be a small questions. Then there will be two concepts, channel length modulation and body effect, that we will see. So first question is, how many charge carriers are there in a MOS? What is the answer? How many charge carriers are there? Only one. Only one. What is that? In case of PMOS, what is the charge carrier? Holes. And in case of NMOS, what is the charge carrier? Electrons. When we studied PN junction, how many charge carriers were there? Two. Because of holes as well, the current was generated. Because of electrons as well, the current was generated. Because of both. But here, in case of NMOS, the current is generated because of electrons only. There is no role of holes in the generation of current in case of NMOS. The current is generated because of electrons only, because N plus and N channel. So because of electrons only. So the current is generated because of electrons only. And in case of PMOS, current is generated because of holes only. But when we studied PN junction diode, the current was generated because of both. Holes were going here and these were going here. So the current was generated because of both. But here the current is generated because of electrons and holes only. So here there is only one charge carrier. And in case of PN junction diode, there are two charge carriers, both electrons and holes. What is the need of oxide layer in MOS? So when we studied MOSFET circuit, what did we study? Metal, oxide, semiconductor. So this was our MOS, metal, then oxide, and then there was this semiconductor or channel, you can say. Here we will be framing the channel. So why there is this oxide layer? What is the use of that? Okay, here there was gate potential, right? Let's assume this I am talking about NMOS. Let's assume I am talking about NMOS. Let's assume I am giving positive potential here. If I give positive potential here, what happens? Here negative potential is induced. First negative is induced, then inversion layer is formed. Why negative is induced? Because here there is positive potential, so electrons will be coming inside. And there are this negative charge and a hole. So this will recombine with the hole. So only negative charge will be left. So this negative charge will be there. So when we apply a small positive potential, what happens? A small negative potential are there across the semiconductor. Now what if this oxide layer was not there? If this oxide layer was not there, what would have happened? These negative charge would have reached to this plate, this metal plate, and would have neutralized it. If the negative charge were reaching this metal plate, then there is no chance that there will be a inversion layer here. Because what would have happened? That battery is supplying electrons, and then all the electrons would have reached to this metal plate. They wouldn't accumulate near the semiconductor. They wouldn't accumulate in the channel. They would have reached to metal. Are you understanding this point? But since there is oxide layer, there will be no electron that will be reaching the metal. So there will be no current. So this gate current will be 0. And since there will be no current, that means in the vertical direction there will be no current. In this direction there is current. Because of this positive supply here, in this direction there is current, but in the vertical direction there will be no current. So because of this oxide layer, these negative potential or electron are not reaching the metal plate. And if they are not reaching the metal plate, we can make the inversion layer. And if the inversion layer is framed, then we can have the current in the NMOS. The drain current would be there. If this oxide layer was not there, then these electrons would have reached to the metal plate, and then gate current only would have been there. There would be no drain current. But we want the drain current. We want the output current. It's not that I am applying a battery and from there I am getting a current. No. So in case of NMOS and in case of PMOS as well, the gate current is always 0. Why so? Because of this oxide layer. If this oxide layer is there, that is preventing these electrons and the negative charge to reach to the metal plate. And that will frame our inversion layer and we get the drain current. So that's why oxide layer is important. So this I will write in the theory. So I will pause the video and write it down because it will just waste your time. Yeah, so this is what I wrote. Because of this oxide layer only, the electron and the negative charge near the semiconductor is not reaching the metal plate, and we are able to frame the channel. And this channel helps in generating the drain current. Understood? Now the third question, why do we use MOSFET in enhancement mode of operation for amplification? That I have already explained you. Because what did we need as an amplifier? That I apply a certain input voltage and then I get a output that is depending on the input voltage. So in depletion type of MOSFET, the channel was already present. Even if you don't apply any input, you get some output, you get some drain current, and that is not desirable. Like even if I am not applying any input, still I am getting some output, that is not desirable. So here in enhancement type of MOSFET, the MOSFET doesn't conduct for zero input voltage. For conduction, your VGS should be greater than VT, and the drain current depends on the applied input voltage only. So applied on VGS voltage only, my drain current depends. So here I will apply some VGS voltage. Let's assume this is VG, this is VS, or I should write this is gate potential and this is drain potential. This is gate potential, this is source potential, then this is drain potential and this is source potential. So from drain to source there is a current, and if I am applying some VGS voltage here, from drain to source I will get some current and that will go to my output. Well and good. There will be a R node resistance as well, which I haven't shown. From where this R node resistance will come, that we will check. I am saying that there will be one R node resistance as well. Now from where that will come, let's check that. So now our next concept will be channel length modulation. So ideally what we have studied? We have studied this graph of, okay, I will not show this. So ideally we have studied this, that for increasing VDS, the current will increase linearly and then it saturates. This is what we have studied. So what we have studied, for VDS greater than VD sat, the current saturates. Current saturates. But practically what happens, when you increase VDS, it increases linearly, then it nearly saturates. That means it will rise a bit. It is not saturated. Saturated would have been like this, but it will rise slightly. So even after the saturation voltage, the current doesn't saturate. It rises slightly, very low. So this I will write. Practically for VDS greater than VD sat, current rises slightly. So this was our channel. So initially when you, what should I color? Yeah. So initially let's assume this is our channel. This is our channel. When you keep increasing VDS voltage, what happens? The channel start getting trapezoidal like this, and at one point the channel becomes something like this. So the time when the channel becomes something like this, this is our saturation voltage only. This is our VD set. So the drain to source potential or the drain potential, when the channel is depleted of charge carriers from drain side. The VDS potential when the channel is depleted of charge carriers from drain side. From drain side, it is completely depleted. So that potential only is known as VD set. And then what did we say? That I further increase VDS. If I further increase VDS, what will happen? My channel will be something like this. So now my reverse bias is getting increased, but the number of charge carriers are getting less. The number of charge carriers are getting less, but my reverse bias is getting increased. So reverse bias is strong, but charge carriers are less. So eventually I will have a saturated current. So there is one phenomena is saying that the electric field is strong, so the current should increase. But the other phenomena is saying that there are less charge carriers, so the current should decrease. One is saying more electric field, current should increase. One is saying there are less charge carriers, the current should decrease. So what happens? The current saturates. But in practical sense, what happens? The electric field is more dominating. In practical sense, the electric field is more dominating. They are saying that the electric field is strong, so it will increase the current, but very slightly, not linearly, very slightly. Like if this was the linear waveform increasing, and if this was the linear waveform, then this would be the practical waveform. If this was the ideal waveform, then this would be the practical waveform. So what is the reason? The reason is the same. Why it is happening? The reason is the same, that when you keep on increasing VDS, what happens is that the electric field is very strong. So because of that very strong electric field, the current slightly increases. Previously I was saying that the electric field is strong, but the number of charge carriers are less, so the current saturates. But when I see the practical scenario, I observe that even if after the saturation voltage, even if I am increasing the VDS, still my current is increasing, but very slowly. This is what I observe when I do the practical things. So this I can write, and this here I will show as well, that this depletion width is getting increased. When VDS is greater than VD set, depletion width is getting increased. If it is getting increased, then there will be strong electric field, and this strong electric field will increase the current slightly. Increases the current slightly. Okay, so this was the practical scene, and this was the ideal, this is the practical. Actually, I have shown this slope to be high. This slope is high. This is just to show you, but in actual the slope will be very low. It will be like this only. But this is just to show you the difference between ideal and practical graph. I am showing the slope to be very high, but actually it will be very low. And if you increase the graph, if you increase this graph in negative direction, what will happen? At some potential, if you increase the graph like this, at some potential the current will be 0. This potential is known as early voltage. We will derive the formula. We will see what do I mean by early voltage. But before that, let's write down the condition for ideal case. What is the current for ideal case in saturation mode? Linear mode we are not talking about. Now we are talking about only saturation mode. So what is the current in saturation mode for ideal case? The current is mu n cox w by 2l VGS minus VT square. That is a constant for fixed VGS. Constant for fixed VGS. Here also VGS are fixed for both of the cases. For both the cases, VGS is fixed. Constant for fixed VGS, independent of VDS. Independent of VDS. That means even if you increase VDS, my current will be constant. This is the ideal case. This is the ideal case. Now there is a term called drain source on resistance. Drain source on resistance. There is a term called drain source on resistance. So from here you are applying VDS voltage, and here you are, let's assume this is a black box. This is a black box. So you have two nodes. At this port you can apply VGS, at this port you can have VDS, and from the VDS you can have your output current ID. If you are not able to understand, this is my MOS, right? MOS is there in a black box. It is kept closed in a black box. This is my gate. This will be my source, right? This will be my source only. This will be my drain, and this will be my also my source. Gate source, drain source. This is my black box, right? VGS, VDS, and there is this black box. So if I apply VDS, I will get some current IDS, ID. This is what I am talking about in saturation region. So I keep the value of VGS and VDS and VT such that my MOSFET is working in saturation region. Now I am taking the ideal case. In ideal case, what do I observe? If I keep on increasing VDS value, there is no change in ID. What is the formula of resistance? R ohm that I am talking about. I shouldn't write R ohm, it should be RDS only. Drain to source ohm resistance in saturation. In saturation. So what will be that RDS value? That RDS value will be del VDS. Okay, this is written wrong actually. Del ID upon del VDS. No. This will be 1 upon RDS. 1 upon RDS. So what will be my RDS? The change in VDS voltage and the change in ID voltage. Even if I change it, even if I change this, the current is constant. The current is constant. So dial ID is 0. Whatever the change I make in dial VDS, let's assume I make the change in dial VDS, that is X. But the change in current ID is 0. That means the resistance would be infinity. Are you getting this point? So in case of saturation region, the drain to source own resistance, or you can say output resistance. You can say output resistance. So in case of saturation region, for ideal case, output resistance is infinity. So dial ID by dial VDS is 0, or you can say that here the slope is 0. That means dial ID by dial VDS will be 0. The slope is 0. That shows that the resistance is infinity. But that is the case when there is no channel length modulation. That means when the case is ideal, for ideal case. But let's check for practical case. So practically what is happening? So this was our source, and then this is our channel. This is happening at VDS equals to VD set. Now if you further increase VDS, what happens? Your effective channel is getting reduced. Your effective channel is getting reduced. Initially the channel length was L. You can say that in my complete channel there are some charge carriers. In my complete channel there are some charge carriers. Now your effective channel length is reduced. Here I showed you. Your effective channel will keep on reducing. So now your effective channel is reduced. Let's assume it is reduced by delta L. It is reduced by delta L. Your effective channel is reduced by delta L. Right? Now what will be your current equation? The current equation will be mu n cox W by 2L. But instead of L, I will write L minus delta L. Why will I write L minus delta L? Because your effective length is reduced. That's why I will write L minus delta L. And then the same VGS minus VT whole square. So I will write down this equation again here because we are doing the derivation. So what is the current? That is mu n cox W by 2. The length is reduced, L minus delta L, and VGS minus VT square, that is same. If I keep this L out, what will happen? Mu n cox W by 2L 1 minus delta L by L into VGS minus VT whole square. Mu n cox W by 2L VGS minus VT whole square. What do I do with this? 1 minus delta L by L. I can write it like this: 1 minus delta L by L inverse power. Are you agreeing with this point? 1 minus delta L by L inverse power. Well and good. I can write it in this manner. Now what is this? This is ID set in ideal case. ID set in ideal case. Mu n cox W by 2L VGS minus VT whole square. So this is ID set in ideal case. ID set ideal. ID set ideal. Now look, this channel length is reduced, but this delta L is very less. I am saying that the channel length is reduced, but delta is not that much large. This delta is very less. So this complete portion will also be very less. This complete portion will also be very less. So one approximation, you know, that 1 minus x to the power minus 1 can be approximated to 1 plus x, right? If x is very low, it can be approximated to 1 plus x. So similarly you can do, that is delta L by L. So this is, I am getting ID set. ID set when there is channel length modulation. Channel length modulation. Why it is called channel length modulation? Because here the channel length is getting changed. That is channel length modulation. Now there is one thing. This delta L by L is proportional to VDS. Are you agreeing with this point? As much more positive voltage you apply, if you increase VDS, what will happen? Your channel will be more depleted. If you increase VDS, your channel will be more depleted. Your delta L will increase. If you increase VDS, your channel will be more depleted. That means your delta L will increase. So delta L by L is proportional to VDS. If you remove the proportionality constant, you get delta L by L is equals to lambda VDS. Delta L by L is equals to lambda VDS. This is equation 1. This is equation 2. So here delta L by L you can put here. I am adding a page. So what will be your ID set when there is channel length modulation? That will be equals to ID set for ideal case ID set for ideal case and 1 plus delta L by L will be replaced with lambda VDS. Lambda VDS. This will be the formula. So ideal current only, but here it is linearly depending on VDS. 1 plus lambda VDS. What is lambda? Lambda is known as process technology parameter. Lambda is some process technology parameter. Technology parameter. What will be the unit of lambda? What is the unit of 1? Unitless. So if this is unitless, something in addition will also be unitless. So this also has to be unitless. So what should be the unit of lambda? Voltage inverse. Because voltage inverse into voltage, that will make it unitless. So lambda should be voltage inverse. So unit of lambda is voltage inverse. So this is what you understand, that this is the expression. So this is only you need to remember. Even if you don't remember the derivation, it is fine. But derivation is very simple. Effective length is reduced, so L you can take outside, then 1 plus delta L is there. Delta L by L is proportional to lambda VDS. So 1 plus lambda VDS, you can simply put lambda is the process technology parameter. Understood? Now there is a term called, okay, we will go to early voltage later on, but first let's check this drain to source on resistance for saturation region. Drain to source on resistance for saturation region. One more condition is there, channel length modulation is present. Now the channel length modulation is present. What is the formula of RDS? RDS is 1 by del ID upon del VDS, right? Or you can write del VDS upon del ID, or I can write 1 by del ID upon del VDS. You have to differentiate it with respect to VDS. What do you get? You have to differentiate it with respect to VDS. What you will get? This is a constant quantity. So that will come as it is, ID set ideal. If you differentiate this, what you will get? 1 is constant, it will be 0. 0 plus lambda is constant, it will come outside. VDS, differentiation of VDS with respect to VDS, 1. So here you will get 1. So if you del ID upon del VDS is lambda ID set. So what you will get? 1 upon lambda ID set here. Simple differentiation is there. ID set will come outside, and differentiation of VDS with respect to ID. Sorry, del ID upon del VDS. Differentiation of ID with respect to VDS will give you lambda here. That will be 1 upon lambda ID set. This is for ideal case. So if they are asking you RDS value, if they are asking you the output resistance in saturation region, if they are asking you the output resistance of MOS, what you will do? 1 upon lambda IDS. That's it. And if lambda is 0, that means no channel length modulation. Lambda 0 shows no channel length modulation. Then your R0 will be infinity. So basically, this is the ideal case only. This I am talking about ideal case. So in ideal case, lambda will be 0. This was ideal case. This complete was ideal case. So in ideal case, your lambda will be 0. There will be no channel length modulation and your R0 will be infinity. Well and good. Let's move on to one more concept, that is early voltage. What is early voltage? What is your ID set when there is CLM present? That is equals to ID set ideal into 1 plus lambda VDS. This is your ID set, right, in channel length modulation. When will this current be 0? To put this current equals to 0, ID set in channel length modulation. To put this current equals to 0, what should happen? 1 plus lambda VDS should be 0. VDS will be minus 1 by lambda. So the value of VDS, at which the drain current becomes 0, that is known as early voltage. Early voltage. So your early voltage is 1 by lambda. And in the graph I showed you, what did I show you in the graph? If you increase it in previous, this early voltage will be. Conceptually it will never be used. Conceptually early voltage will never be used. But sometimes in the question what they can do, they can give you the value of VA. That they will say that your early voltage is some 200 volts. Early voltage is some 200 volt. Then what you will think, okay, my lambda will be 1 by 200. So lambda is there. From there I can find the value of R0. That will be 1 by lambda ID set. So 1 by lambda is basically 200 by ID set. ID set in ideal case. In ideal case I can find ID set. Let's assume that is 0.02. So your R will be some 10 to the power 4. R0 will be some 10 to the power 4. So in the question it will be sometimes used. So they can give you the early voltage. That early voltage is some 200 volt. So from there you can find the value of lambda, and from there you can find the value of R0. So in questions it can be used. So that's why I told you here. So what is early voltage? The negative value of VDS at which the drain current becomes 0 when channel length modulation is present. Well and good. That is early voltage. Yeah, hi guys. So you have surely watched these three topics, right? In this particular video, we have studied these three topics: MOSFET circuit symbol. Then we saw some important questions like what is the use of oxide layer, and like why do we bias the MOSFET in enhancement mode for amplification, and some more questions were there, right? So these topics we have seen, and then we studied about channel length modulation. And because of channel length modulation, what we saw, there was a change in the equation. Mu n CX W by L VGS minus VT whole square multiply with 1 plus lambda VDS, and that is reflecting into the output resistance 1 upon lambda ID. So that we have seen, right? Now we will solve some questions, and after that we will study the concept of biasing. That when we make an amplifier, how do we bias our MOSFET? So that we will study, and also we will study a very important concept of transconductance. Okay, so let's get started. Hi everyone, so now we have studied most physics. Now it's time to solve an assignment. So there will be 4 to 5 questions there. So let me show you the questions. This is the first one. A MOSFET is given. You have to find V naught for two conditions. First, considering R equals to 1 kilo ohm, and second one R equals to 4.5 kilo ohm. Then there will be these 6 configuration. 2 configuration are there more. So you have to find the region of operation. Mu and Cx value is given, W by L value is given, Vt is given. These configuration are given, values are given, Vgs value is given. So like that. You have to find the region of operation. 4 configuration, fifth, sixth configuration. The next one, this is the third question. You have to find that drain current of MOSFET. Drain current you need to find. That means this current you need to find. Drain current. These configuration is given. All those values are also given. Here also you need to find the okay. Here you need to find the RS value such that your MOSFET is working in saturation region. So how will you find that? You can try it. And then here you need to find the bias current in the transistor. What do you mean by bias current? Drain current only. So again you need to find the drain current only. So here again you need to find the ID value. I guess that's it. Yeah. So these questions are there. We will solve one by one. You might not be able to solve it if you are solving it for the first time, because if you are just watching the video of MOSFET for the first time, you might not be able to solve it. No worries. Even when I was a student, I was also not able to solve it. So let's start with the first question. Slowly you will develop the approach. Let's start with the first question. This is R equals to 1 kilo ohm. So we will take two conditions one by one. First we are taking R equals to 1 kilo ohm. So let's take R equals to 1 kilo ohm in the next page. This is circuit A. I will remove this R. This is 1 kilo. Now you don't know in which region MOSFET is working. You have the value, you have VGS value. This is gate, this is drain, and this is source. If there is no fixed potential, we have to assume, right? So we have assumed, like we have to assume in the given sense only. What is the given sense? What is the general sense? I told you what is the general sense. The general sense is, क्या हो रहा है writing pad? Yeah. So what is the general sense? General sense is this is gate, this is source, and this is drain, right? So we have to assume it in that same manner. Yeah. So what is the VGS value given? VGS value is 2 volt. What is the VDS value? You don't know, but that is V naught because source is grounded only. VDS is, and VT is 1 volt. VT is 1 volt. Now, can you tell in which region the MOSFET is working? No, you don't know in which region MOSFET is working. So you have to assume. We will start by assuming this is working in saturation region. So this is my way. I always assume in saturation region. Then I see if it is working in saturation region only, and then I will decide. So this is my way, that I always start by assuming it in saturation region. You can start from linear region as well, but my suggestion would be always start from saturation region. So let MOS is working in saturation region. Let MOS is working in saturation region. So what will be your ID? What will be the ID? ID value will be mu n Ux W by 12 VGS minus VT square. I guess this value is given mu n Cx W by 12. That would be 100 micro. So mu n Cx into W by L, that is 2 milli actually. Okay, I will write down one by one. Mu n Cx is 200 micro into W by L is 10 by 2. Always write down this micro, milli, kilo, always write it down. When you are solving the problem of MOS, always write it down along with. What is the value of VGS? That is 2. And what is the value of VT? That is 1. So what do you get? You are getting 1 milliampere. ID value you are getting 1 milliampere. Are you agreeing to this point? ID value is 1 milliampere, right? This value you got 1 milliampere. Now if this current is 1 milliampere, what will be the V naught value? What is V naught value? V naught value is 5 minus 1 kilo ohm into 1 milli. That would be 5 minus 1, that would be 4 volt. So V naught value came out to be 4 volt. But this is not your final answer. Now what did you do? You assumed here. You assumed MOS to be working in saturation region. So now you have to recheck if the assumption is correct or not. So what did you assume? You assumed the MOSFET to be working in saturation region. So now we will check in what region our MOS is working. So our V naught value is 4 volt. So now what is our VGS? VGS is fixed. That was 2 volt. What was our VT? VT was 1 volt. So what is my V overdrive? I told you what is V overdrive? V overdrive is VGS minus VT. V overdrive is VGS minus VT. I don't remember if I told you about this term or not. So V overdrive is VGS minus VT. Just nothing, just a term that is given to it. V overdrive. Just a simple term, nothing else. So V overdrive is 2 minus 1, that is 1 volt. So 4, and now what is VDS? VDS is 4 volt. Here VDS is equals to V naught only. VDS is equals to V naught only, that is 4 volt. So here what do you see? That VDS is greater than VGS minus VT, or directly we can write VDS is greater than V overdrive. What do you understand by that? If VDS is greater than V overdrive, what do you understand by that? That MOS is in saturation. Saturation. So that means assumption, the assumption that we made, assumption correct, right? So the assumption that we made, that is correct. So if our assumption is correct, that means what is the final answer? What did they ask to find? You have to find the value of V naught. So V naught came out to be 4 volt. So here your final answer is V naught is 4 volt. Now take the condition of R equals to 5 kilo, sorry 4.5 kilo. If R is 4.5 kilo, what will happen then? R is 4.5 kilo. What will be your ID? So again what I will do, assuming, what will I assume? Assuming saturation region. Saturation region. Again I will assume saturation region. What will be my ID? ID will be same value. ID will be same. Why so? Because ID depends on VGS minus VT, and VGS minus VT is fixed here. Or if you don't want to do it, you can start mu n Cux. Again I am assuming it to be saturation region. Mu n Cux W by 12 VGS minus VT square. What is mu n Cux W by 12? That is 200 micro into 10 by 2. 200 micro, W by L is 10 by 2. What is VGS? VGS is 2, VT is 1. So the current came out to be 1 milliampere. If the current is 1 milliampere, if this current is 1 milliampere, tell me what will be the value of V naught? V naught will be 5 minus 4.5 into 1, 4.5 kilo ohm into 1 milli, right? So V naught will be 0.5 volt. V naught will be 0.5 volt. Now, what will be the value of VDS? VDS will be VDS, drain to source. VDS will be V naught only, and that is equals to 0.5 volt. What is VGS minus VT? VGS minus VT. What is the value of VGS minus VT? VGS is 2 minus VT is 1 volt. Now what do you see here? Here VDS is less than VGS minus VT, right? Here VDS is less than VGS minus VT. That means it is working in linear region. This is working in linear region. So the assumption that we made, that is wrong. This is wrong. So assumption is wrong. What did we do? First we assumed that it is working in saturation region. So for saturation region we know the current equation. We applied that current equation. Then we got to know, after applying the current equation, we found the value of V naught. Then we got to know VDS value is 0.5 volt. So based on that, our VDS is less than VGS minus VT. That means our MOS is working in linear region, not in saturation region. So assumption is wrong. Now we will make another assumption. What assumption we can make? Now we will make an assumption that our MOS is working in linear region. Now you will say, sir, if it is not working in saturation region, it is certain that it should be working in linear region. So why we are calling it as assumption? It is assumption only, because it is not sure that it is working in linear region only. If it is not working in saturation, it can be in cutoff as well. So now you will write assuming linear region. You are not very sure that is linear region only. So again you will assume only, and then you will find the value of V naught, and then you can comment if your assumption was correct or not. Are you getting this point? Like I have seen many people directly write that now MOSFET will be working in linear region. So now we will apply linear region equation. But whether it will be working in linear region or not, that will depend on the V naught value that you get. So you can't really say that certainly it will be in linear region. No, assuming it to be in linear region. So again you will assume it to be linear region, in linear region, and then you will find the value of V naught, and then you can comment assuming linear region. Okay, so what is the equation in linear region? Do you remember what is the equation? Mu n Cux W by L VGS minus VT into VDS minus VDS square by 2. This is the equation, right? You should be able to remember. Slowly you will remember if you don't remember. Okay, what is the value of ID? Look, do you know the value of ID? No. In case of linear region, you don't know the value of ID. Do you know the value of VDS? No, because VDS is also V naught. So there are two unknowns. But one thing you can see here is that 5 minus V naught by 4.5k is equals to ID. If this is ID, that means the same current is flowing through this resistance as well. So 5 minus V naught by 4.5k is equals to ID only. Are you getting this point? Simple network analysis here, right? So 5 minus V naught divided by 4.5k. I will certainly write k here. Why so? Because of the units. Unit पे गड़बड़ हो जाएगा, तो k लिखना ही है. We have to write k. Here I am writing mu and Cux. Then I will certainly write 200 micro into 10. What is VGS minus VT? That is 1 only. Because VGS is 2, VT is 1. That is 1 only. Into VDS is V naught minus V naught square by 2. Now my complete equation is in V naught only. Are you getting this point? So that's why I replaced ID with V naught. 5 minus V naught by 4.5k. So from here, what do you get? This is 2 milli 4.5 kilo. Look, what I will do, this value is 2 milli, and if I multiply 2 milli into 4.5k, then k and milli will be cancelled. K is 10 to the power 3, milli is 10 to the power minus 3. So they will make 1 only. So that will be cancelled. So that advantage I will take. 5 minus V naught, 4.5k into 2 milli, basically it will be 9. V naught minus V naught square by 2, right? So this equation we can solve. 4.5 V naught square, this is 10 V naught plus 5. V naught will be 10 plus minus B square minus 4AC, 100 minus 4AC. 4 into 4.5, that will be 9 into 4 minus 4.5, that is 18. 18 into 5, 90 by 2A by 9. Now you will solve it and you will get two values of V naught. So which value you will pick? Let me see the final answer. I might have written it. So what are the two values we get? 1.46 and 0.76. 1.46 volt and 0.76 volt. Two values we are getting. Now the question is which value you will take. So V0 value here I will write. We are getting two values of V0, 1.46 volt and 0.76 volt. So which value you will take? How will you decide? If let my V0 is 1.4. If my V0 is 1.4 volt, what is my VGS minus VT? That is 1 volt. So here, and V0 is equals to VDS only in our question. So here VDS is greater than VGS minus VT. That means it should go into saturation. But it is not in saturation. That we have already seen by the previous analysis. By the analysis here, what we got to know? That it is in linear region. It is certainly not in saturation region. That we have already seen. That it can't be in saturation region. So this case is not possible. This case is wrong. Because we already know that our MOS is not in saturation region. It can be in linear, it can be in cutoff, but certainly not in saturation region. So that condition is eradicated. Now let's talk about the second condition. If I take V0 equals to 0.76 volt, that is equals to VDS. What is the value of VGS minus VT? That is 1 volt. So here what do you see? VDS is less than VGS minus VT. VDS is less than VGS minus VT. That means it is in linear region. And the assumption that we made, that is correct. Assumption correct. So our V0 will be 0.76 volt. So that will be the answer. So many times these kind of questions are asked. You don't need to worry about these kind of questions. You don't need to what do we say, panic when you see these kind of questions. The general way is first assume the transition to be in saturation region, then find the conditions. Then you get to know your assumption is right or wrong. If it is correct, well and good, question is solved. If it is wrong, then make another assumption. The second assumption should be, it should be in linear region. Then you make that assumption, then solve the question. If you are getting two values, then pick that solution only which makes your assumption correct. So here this assumption was being corrected. So our V0 value was 0.76 volt. In the examination, within 2 to 3 minutes, you will be able to solve these problems. No need to worry. Here I am explaining. That's why it is taking time. Let's move on to the next problem. Solve this problem by your own, then only see the solution. Pause the video and solve this. Yeah, so let's solve this problem. So here they have given the current direction. Current direction is downward. And one thing I know that this is NMOS. Why so? Because arrow is outward. So I know this is NMOS because arrow is outward and current direction is given like this. That means this has to be drain. In NMOS, what is the direction of current? Drain to source. And in case of PMOS, what is the direction of current? Source to drain. That we have to remember. Electrons were going into the drain. So direction would be drain to source. So the current direction is drain to source. So the upper one is drain, lower one is source. First thing I saw that this is NMOS. Second thing I saw that the current is going from up to down. That means drain to source. That's it. And this certainly has to be gate. What is the VGS value here? 3 volt. VT value must be given in the question, that is 1 volt. Let me recheck. 1 volt. Any other information you have? You have the ID, current ID, that is given 150 microampere. So this is the all information you are having. Now to comment on that, you need the value of VDS and you don't have that. So first what you will do, you will assume it to be in saturation region. Let MOS in saturation region. Let MOS is in saturation region. If it is in saturation region, what will be ID? ID will be mu n. I will again and again write this formula so that you memorize it. Mu n Cux W by 2L VGS minus VT whole square. What is the value of mu n Cux? Here it is 100 micro. W by L is 10 by 2. VGS value is fixed minus VT value is 1. So what do you get? ID value you get is 200 micro ampere. So what did you get to know here? That if the MOS was working in saturation region, the current would have been 200 microampere. But the given current is 150 microampere. That means it is not working in saturation region. What do you do? ID versus VDS curve you have studied, right? If your VDS was such that it is working in saturation region, if your VDS was such that it is working in saturation region, then your VDS would have been somewhere here. Because in the saturation region, the current is maximum. The current is saturated. That means this is the maximum current that it can take. This is the scene. This is the maximum current that it can take, which is 200 microampere. For a particular VGS value, this is the maximum current it can take. VGS is fixed, that is 3 volt. So for a particular VGS value, this is the maximum current it can take. But now it is taking 150 microampere. That means VDS should have been somewhere here, right? This is your VDS operating. Operating means at which this transistor is operating. So this is your VDS operating. What is that region? Linear region. So your MOS, here you can say MOS is not in saturation but in linear. Did you understand this question? First you solved it, you found the current came out to be 200 microampere. So that you got to know that for a VGS value of 3 volt, this is for fixed VGS. Here VGS is fixed. For a VGS value of 3 volt, your drain current should be 200 microampere. But the current is lesser, that means it has to be in linear region. That's it. So this was the first question. Let's take up the next one. What they are asking in the next one, I guess they have changed the data here. 2.5 and 200 microampere is coming. 200 microampere is coming. This is 2.5 volt. And from here 200 microampere is coming. Do you have the idea of VGS value? No. And what will be drain, what will be source? The current is coming like this and it is NMOS, so it has to be drain to source, and this will be gate only. The current will always be flowing in drain to source, right? Yeah. So ID value is given 200 microampere. Do you have the VGS value? Nothing you have. Again, let saturation region. So if it is saturation region, then ID would be equals to ID. Okay, I will write down the formula again and again so that you remember it. ID will be equals to mu n Ux W by 2L VGS minus VT whole square. So 200 micro is equals to, I will write down this micro for sure. 100 micro into W by L is 1 by 2 VGS minus VT whole square. So from here VGS value came out to be 2, right? Not 2, sorry, 3. Yeah, VGS value came out to be 3. So from here VGS came out to be 3 volt. Now your VGS is 3 volt. So if it is in saturation region, your VGS should be 3 volt. But let us check if our assumption is correct. VGS is 3 volt. What is VDS? VDS is 2.5 volt. What will be V overdrive? VGS minus VT. VGS minus VT. That will be 2 volt. Here VDS is greater than V overdrive. That means saturation region. And if it is in saturation region, that means your assumption is correct. Assumption correct. Your answer is also correct. Your VGS is assumption is correct. That means it is working in saturation region only. And this is your final answer. They did not ask VGS value or anything. They just asked the region of operation. And here linear region was the answer. Right? Let's move on to the next one. This is very simple actually. Right? I can solve it here only. Now you will say, sir, now the current direction is not given. How we will decide which is drain, which is source? You can decide, right? If this potential is x, what will be this potential? X plus 4. So the one which is at higher potential, that is drain. In case of NMOS, the one which is at higher potential, that is drain. Do you remember these points? I will revise it once again. ध्यान से सुन लो, ठीक है? सभी ध्यान से सुनेंगे. In case of NMOS, the one which is at higher potential, that is drain. Lower potential is source. The current flows from drain to source, higher potential to lower potential. That's it. In case of PMOS, the one which is at higher potential, that is source, and one which is at lower potential, that is drain. The current flows from higher potential to lower potential, that means from source to drain. That's it. Very easy. You can remember it, right? Yeah. So one which is at higher potential, that means that will be drain. This will be source. Drain, source. And certainly this will be gate only. So here you can see what is the value of VDS? 4 volt. What is the value of VGS? 2 volt. What is your V overdrive? VGS minus VT, that means 1 volt. So VDS is greater than V overdrive. What is the answer? Saturation region. That's it. Very easy, very straightforward. You can solve this one here as well. What is the value of VDS? 2 volt. What is the value of V overdrive? VGS minus VT. Look, you will say that now, sir, gate is at higher potential. While designing drain and source, there is no meaning of VGS value. Only by VDS you are deciding. People may say that, sir, this is at the highest potential, so this should be drain. No. This will always be gate only. Now the task is between these two. This is at x, this is at x plus 2. So this will be drain, this will be source. What is your VDS? 2 volt. What is your V overdrive? That is VGS minus VT. 4 minus 1, 3 volt. So here VDS is less than V overdrive. What does this signifies? It is in linear region. Well and good. So linear region, saturation region. Okay. Now this question. Here you don't have potential of anything. You don't know the potential of drain, you don't know the potential of source. What will be drain, what will be source? Here you have to assume. If there is no potential given, you have to consider that this will be drain and this will be source, the general form. In previous questions, you had the potential of someone. You had the potential of drain and source, anything. But here you don't have the potential. You have to assume that upper one will be drain, lower one will be source, because this is NMOS only. Because the arrow is outward, this is NMOS only. Here again I will assume this is drain, this is source. Let's assume this potential is X, or forget about X. This potential is VD, this potential is VS, and this potential is VG only. What is the value of VDS here? VDS, that is VD minus VS only. What is the potential of VGS here? What is the potential of VGS? That is VG minus VS. But you can write down VG in terms of VD. This is VG minus VS only. But what is VG? VG is VD plus 1.5. VG is VD plus 1.5. Are you agreeing to this point? VG plus 1.5 minus VS. You can write VGS is 1.5 plus VDS. Are you agreeing to this point? VGS is 1.5 plus VDS. Did you understand this point? Right? VG minus VS, then I write down the value of VG, that is VD plus 1.5. So it is 1.5 plus VDS. And what is VT? VT is 1 volt, that is given. VT is 1 volt is given. What is the value of V overdrive? V overdrive is 0.5 plus VDS. So here what do you see? VDS is less than V overdrive. Are you agreeing to this point? Because V overdrive is 0.5 plus VDS. So it is certainly greater than VDS. So here V overdrive is greater. So what does that implies? That implies that this is linear region because V overdrive is more. VDS is small, that means it is linear region. Did you understand this point? How did I solve it? I just found the value of VDS, VGS and VT. That's it. Here I will have the same target. What is the value of VDS? Okay, before this thing I will tell you one interesting thing, that is, so while defining the saturation region, what do we do? VDS should be greater than VGS minus VT, right? This is what we do. What is VDS? That is VD minus VS. What is VGS? That is VG minus VS minus VT. Source to source get cancelled. So VD should be greater than VG minus VT. That's it. There is no role of source. In case of NMOS, there is no role of source for defining the region of operation. Same in case of PMOS. In case of PMOS, what will happen? VSD should be greater than VSG minus mode of VTP. Right? So Vs minus Vd should be greater than Vs minus Vg minus mode of Vt, whatever it is. Vs would get cancelled. Minus of Vd should be greater than minus of Vg minus of mode of Vtp. Then Vd should be less than Vg plus mode of Vtp. Simple mathematics I have applied. This minus minus sign, minus minus got cancelled, so arrow sign will also change. So this is also the condition. So and these are the conditions. So here what do we understand? That there is no role of source potential for defining the region of operation. But still we write in this manner because it is easier to remember. Here if I had told you these formulas, you would have forgot, okay, where will this arrow sign come, how will the arrow come, when there will be plus, when there will be minus. So this I don't wanted you to go through. So that's why I told this formula VDS is greater than VGS minus VT. But you have to remember that there is no role of source potential while defining the region of operation. Are you getting this point? If your VGS is greater than VT, that's it. If your VGS is greater than VT, then your transistor is on and everything is in your control. Whether it will be in saturation or in linear, you can directly know it by the potential of VD and VG. If it is on, if it is not on, then it certainly depends on source potential as well, because VGS has to be greater than VT. Right? We have understood everything. So here just one interesting point I wanted to deliver, that source has no role until VGS is greater than VT, because before VGS less than VT, the transistor is not even on. After that, if VGS is greater than VT, then only these things will happen. And here by default we consider that VGS is greater than VT. Here we had to consider that VGS is greater than VT. If this was the case that VGS is less than VT, less than 1 volt, then everything that we have studied, that is wrong. There is no meaning of that. So we have to consider, by default we consider that VGS is greater than VT. So I should have mentioned it in the question that your VGS, you need to consider VGS to be greater than VT. Otherwise the transistor will be off. Yeah. So here as well VGS is greater than VT, so your transistor is on. That we have to certainly consider. So your VDS is VD minus VS. What is your VGS? Here what is your VGS? Your VGS is, what is your VG? VG is VD plus 0.5. VD plus 0.5 minus VS. So VGS is VDS plus 0.5 volt. What is VT? VT is 1 volt. What is V overdrive? V overdrive is VGS minus VT. That is VDS minus 0.5. Which one is larger? VDS minus 0.5. Which one is larger? VDS is larger, right? Let's assume VDS is 1 volt. So what will be your V overdrive? That will be 0.5. So VDS is larger. So VDS is greater than V overdrive. That means this is saturation region. Are you able to understand this point? But one thing I should have mentioned, that your VGS is greater than 1 volt. In all these questions here, I will write it with the yellow pen because this is in the question only. Let VGS is greater than 1 volt. So this we have to consider. Okay, well and good. Let's move on to the next problem. So here in the first two questions, what did we learn? We learned about how do we find the region of operation, how do we apply the drain current formula, how do we apply the saturation current formula, right? So these formulas we have applied and then we found the region of operation. Now we will move to better questions. Here you again need to find the drain current of MOS. Do you know the region of operation? Again we don't know. What will be drain, what will be source? Do you know the potential of this point? No. Do you know the potential of this point? No, you don't know. You know the potential of this point? Yeah, but you don't know the potential of this point. We will again consider by the same formula, that is this should be drain, this should be source. When it will be interchanged, I will tell you in the question itself. But here we have to consider by the general way that upper one will be drain, lower one will be source. Because we don't know the potential of drain, right? You have to find the drain current of MOS. This is the question now. Tell me one thing, what ID will be equals to? Can you write one equation, that is ID plus V naught by 10K plus V naught minus 6 by 20K is equals to 0. Is that equation correct? Yeah. Outward current, this outward current, this is also outward current, V naught by 10K, this is also outward current, or this is also outward current. Addition of outward current is equals to 0. Simple KVL, I am applying, sorry, simple KCL, I am applying KCL at node V naught. KCL at node V naught. This is what I did. I will not call this one as equation 1 because I need to find the ID value. So for ID value, I will write 6 minus V naught by 20K minus V naught by 10K. This is my I naught value. Again, you don't know the region of operation. Again, you have to assume. Okay, so we will start by assuming. What I will do, let MOS is in saturation. MOS is in saturation. Then what will be ID value? ID value will be mu n Cx W by 2L. Now I am not going to write the formula. Okay. VGS value do we have? VGS value is 3 volt. VGS minus VT square. ID value came out to be 200 micro, right? Or 200 micro. ID value came out to be 200 microampere. Now, if it is 200 microampere, what will be the value of V naught that we can find? So 200 micro is equals to 6 minus V naught by 20K minus V naught by 10K. 20 will go here. 2 into 10 to the power 4. This will be 2 into 10 to the power 4. This will be 4 only. 6 minus V naught minus 2 V naught. 3 V naught by equals to 2. So V naught will be equals to 2 by 3. So what you are getting? 0.67. When you solve this equation, V naught value we are getting is 0.67. V naught value we are getting is 0.67. What is your V overdrive here? VGS minus VT. That is 2 volt. Right? V overdrive is 2 volt. Here you can see VGS minus VT, V overdrive is 2 volt. What do you see here? That your V naught is equals to VDS only. This is your V naught. V naught is VDS only. Here your VDS is equals to V naught. V naught that is equals to VDS. This is lesser than V overdrive. What does this shows? Linear region. If it is in linear region, your assumption is wrong. So the assumption you made, that is wrong. So this ID, this is wrong, this is also wrong. So now again you have to make assumption. Assuming, what assumption you will make? Assuming MOS in linear or triode, linear region. For linear region, what is the current equation? Mu1 Cux W by L VGS minus VT into VDS minus VDS square by 2. So those who are solving it for the first time, मतलब जो पहली बार पढ़ रहे हैं, they, for them it might seem a bit hectic, like so much of calculation is there, how do we remember all these things? But once you practice enough questions, you will be habitual. The only thing you need to do, first you need to consider, then you need to find the parameters. Not satisfied, good enough, not satisfied, assume the other region. That's it. In the second one, it will be satisfied, that's for sure, right? So yeah, now you have again two variables, ID and V naught, but ID we have wrote down in terms of V naught only. So 6 minus V naught by 20k, 6 minus V naught by 20k minus V naught by 10k. Also you should have good aptitude to solve the problems, like calculation should be better. That's why I am showing you all the calculation, because in these kind of question, calculation becomes a very important part. So mu and Cux is 100 micro, so I will certainly write 100 micro. I will not miss that. Into W by L is 10. VGS minus VT is 2. VDS is V naught only, minus V naught square by 2. Right? So here this is 2 into 10 to the power 4. This is 2 into 10 to the power 4. This is 10 to the power 4. So LCM will be 2 into 10 to the power 4 only. Right? So 6 minus V naught minus 2 V naught, and 2 into 10 to the power 4 will be going here, and this is already 10 to the power minus 4. Are you getting this point? So this will be 20 only. 20. 2 V naught minus V naught square by 2. Well and good. Is there any mistake I have done? W by L is what? 1. Yeah, that's what I was thinking. W by L I have taken here also 1. W by L is 1 here, not 10. So this will be 2 only. इतना आंसर तुम्हें को याद था? Minus V naught square. So V naught square minus 7 V naught plus 6. So V naught, 2 V naught values we will get, I guess, from here as well. But you can tell which value I should take. Here I am getting 1 as well and 6 as well, right? 1 we satisfied over 6, 36, 42, yeah. So from here V naught value we get, two values we are getting, 1 volt and 6 volt. If you take this 1 volt, what will happen? Your V overdrive will be lesser than VGS minus VT, right? If I take V naught equals to 1 volt, okay, I will write if V naught is equals to 1 volt, what is V overdrive? That is 2 volt only. VGS minus VT, VGS minus VT is 2 volt. So here VDS is less than V overdrive, that shows linear region. Linear region, and assumption is correct. Assumption is correct. So your V naught value will be 1 volt. V naught value will be 1 volt. But if you take दो एरो लगा दिए यहाँ पे, if you take V0 to be 6 volt, what will happen? V overdrive will be 2 volt and your VDS will be greater than V overdrive. That shows saturation region, but in the previous part of video we found out that this is not in saturation region. Not in the previous part of video, but in the previous part of solution we found out that this is not in, okay, wait, yeah, this is not in saturation region, right? The MOSFET is not working in saturation region because here when we assumed it in saturation region, it came out to be in linear region. So this is not certainly not working in saturation region. So this cannot be true. So the only option true is this. So your V0 value is 1 volt. That's it. Okay. Let's try solving this question on your own. Now you have the enough aptitude. You can take your time and try solving this question on your own. The question is, the MOSFET is working in saturation region. That is given. If it is working in saturation region, what should be the value of Rs? So now you don't have to assume. It is given that it is working in saturation region. What should be the value of Rs? This you need to find. Tell me what is the potential here. Will it be 1 volt? Can you directly say it that it will be 1 volt only? Yes, I can directly say it will be 1 volt only. Why so? Because there is 0 ampere current here. If it was driving some current, let's assume if my circuit was something like this. 4R, R, this is 5 volt and this is driving some 1 ampere current here. Let's assume this is driving some 1 ampere current here. Can you say this potential will be 1 volt? This is wrong. This potential will be 1 volt. No. If this is not driving any current, then only you can apply the voltage divider. No. Are you getting this point? अगर यहाँ से करंट नहीं जा रहा तभी तो वोल्टेज डिवाइडर लगाओगे. R1 by R1 plus R2 into V in. If it is driving some current, then you can't apply voltage divider. What you will have to do? You will have to assume a voltage V here. So V minus 5 by 4R plus V by R plus 1 ampere is equals to 0. Then you can find the value of V. But if this 1 ampere is infinite, this 1 ampere is not there. If this 1 ampere is not there, then what will be the case? This will be the case. And from here, what will be the value of V? That will be 5V minus 5 equals to 0. V will be 1 volt. Basic network analysis, very basic network analysis. But these kind of concepts we will again and again use. People will every time think that we can apply voltage divider, but we cannot apply. We can only apply if there is 0 ampere current. If the node is driving some current, if there are two paths, then you can't apply voltage division. There is only one path. This node can drive current only here. That's it. Are you getting this point? So that's why we cannot apply nodal analysis here. Here we can apply, but if it was driving some current, we couldn't have applied it. So here this potential is 1 volt, right? This potential is 1 volt. Yeah, so 1 volt is fixed here. So what is the value of VGS? Because if it is in saturation region, it is given. We don't need the value of VDS. VDS की वैल्यू की जरूरत ही नहीं है क्योंकि this is working in saturation region. So we only need the value of VGS. What is the value of VGS? That is 1 minus, let's assume this current is ID, so that will be 1 minus ID into RS. Are you agreeing to this point? Why you are agreeing to this point? Because this is source. What is the potential of source? VG we got to know here, that is 1 volt. What is VS? VS will be ID into RS because this is source, right? This node is source. So VS would be ID into RS. So VGS will be 1 minus ID into RS, right? VT is given 0.5 volt. Now current equation is given already. So what is ID? ID is, here I can write ID is Kn into VGS minus VT because Kn is already defined. Kn is mu n CX W by 12. Kn into VGS minus VT whole square. So ID is 119 micro, that is equals to 4.12 millisiemen per volt milli. What is VGS? VGS is 1 minus 119 micro into RS. This is VGS. 1 minus ID into RS. So ID value 192 into RS minus 0.5 whole square. Now I will directly solve it in gate calculator, or in your main calculator also you can solve. But how will you solve it in gate calculator? What you will do, you will convert this into milli, because milli and milli will get cancelled. So 119 micro in milli, what that will be? 0.119. So 0.119 micro divided by 4.12. 0.119, I guess, I don't think I will be able to show it. So 0.119 milli divided by 4.12 milli. Milli and milli got cancelled. Then I will take under root. So here I am getting 0.169. So 0.17 I can write. This is equals to 0.5 minus 119 micro into RS, because 1 minus 0.5 is 0.5 only, right? Now people will say that Bhaiya, you took the under root, so here plus minus should come, right? Whenever you are taking under root, always take plus sign. We have solved enough question, I have solved enough problems. If I had taken negative sign here, what would have happened? What would have happened if I had taken the negative? So if I had taken the negative sign, what do you mean by that? You are saying that your VGS minus VT is negative. If you are saying, sir, if you take under root, that means plus minus should come. But is that so? Because here you are writing some ID value is there. So ID by Kn under root. This is what you are doing here. And that is equals to VGS minus VT. Now if you are saying plus minus should come. So if it is minus, if you are taking the minus sign here, what will happen? You are saying VGS minus VT is negative. And if VGS minus VT is negative, the MOSFET will not even turn on. So never take the negative sign. Always take the positive sign. So this is one thing that you can note down in your notes, or you can highlight, that you should always take positive sign whenever you are taking under root, because VGS minus VT cannot be negative, right? So many times teachers don't tell this concept, why we are actually taking the positive sign. So positive sign should be taken, that everyone remembers why it should be taken, because VGS minus VT cannot be negative, right? So from here I can directly solve and find the value of RS. Yeah, so in the gate calculator instead I will solve it. Minus 0.5 divided by 119 micro. अरे यार 0.5 minus 0.17 divided by 119 micro into 1000. 2.77 kilo ohm. 2.77 kilo ohm. So this is the value of RS. Well and good. I guess one more question is left. That is also very good question. This was actually very easy question. Just everything was given. You need to find the value of RS. This question also you can try solving. That is a very good question. And where am I getting all these questions from? Because they are NPTEL assignments. From there I am getting these questions. So whatever that is necessary for you, that I am dealing here. Okay. Yeah. So find the bias current in the transistor. So again, ID current you need to find. This value given is 40 kilo ohm. So RR value is given 40 kilo ohm. Now what do you think? This current 100 microampere is the answer. ID is 100 microampere. Is that so? Complete current is coming. Is that so? No. That is true that here there will be 0 ampere current. This is true. But who said current cannot flow from here? Current can certainly flow from here. There will be no current here, but certainly the current can flow from here, right? So let us say this potential is V naught. Let us say this potential is V naught. Then what this potential will be? If this potential is V naught, this potential will be V naught by 2. Say yes or no, right? VDS value is V naught. VGS value is V naught by 2. VT value is 1 volt. Until you know the value of V naught, you cannot decide in which region it is working. So again, you have to assume that it is working in saturation region or linear region. So again, you have to assume. The choice is up to yours. In what region do you assume? Okay. But before that, we cannot have two variables, V naught and ID. So we have to write ID in terms of V naught. So what will be ID in terms of V naught? From upward, 100 microampere current is coming. Here, how much current is going? Can you tell how much current is going in this direction? V naught by 2R, right? You know the potential of this node, you know the potential of this node. V naught minus V naught by 2R. So this current is V naught by 2R. This current is ID. So 100 micro is equals to V naught by 2R plus ID. So ID you can write 100 micro minus V naught by 80K. 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 So if I want to write it in micro only, 100 micro minus, I will also write down in micro only. So what I can do? 1000 by 80, 1000 by 80 V naught micro. Did you understand what did I do here? I have 1 by 80K. I want to write it in micro. So 1 by 80K is similar to 1 by 80 milli. So if I multiply and divide it with 1000, so what I will get? 10 to the power 3 into 10 to the power minus 3. So 10 to the power minus 3 into 10 to the power minus 3. That will give me micro divided by 80. So this is how I converted it in the micro, because here the current was in micro. So I needed all of them in micro only. Or I could have converted in milli. This was also a good way, but I thought of making it in micro. So this is my ID. So my ID will be 100 micro minus 12.5 V naught micro. This will be my ID. Now what we are assuming? We are assuming MOSFET to be in saturation region, or I can assume it to be in linear region, because as far as I remember, it will be in linear region only. But since we are following the same method, so let MOS in saturation. This ID that I found, that is irrespective of linear or saturation, right? This ID that I found, that is irrespective of linear or saturation, because I did not apply any ID equation. I just assume ID as a variable. ID will be equals to mu n Cux W by 2L. So 100 micro divided by 2. VGS minus VT whole square. What is VGS? That is V naught by 2 minus VT. What is VT? 1. Right. Now ID I can replace here. ID is 100 micro minus 12.5 micro V naught, 50 micro, that will be V naught by 2 minus 1 whole square. Now micro will get cancelled, right? Micro, it can get cancelled. 100 minus 12.5 V naught, and this is 50 here. This will be V naught square by 4 plus 1 minus V naught. So 100 minus 12.5 V naught. The calculation is a bit complex, and these kind of complex questions are asked in GATE examination as well. You don't think that this kind of complex calculation will not be asked in the examination. It can be asked. Many times it has been asked. So yeah, you should be ready that these kind of calculation can also come. You should have the patience that slowly I can solve these problems, right? So 12.5 V naught I will put here only. Now this will come here, so 37.5 V naught, and this will come here. minus 50 well and good is equals to 0. कोई मिस्टेक तो नहीं कर दिया है, बस ये डर लग रहा है मेरे को. ठीक है, minus 50. Okay, 12.5 I can take common, I guess. So this will be 3 V naught, right? I can take common. V naught square minus 3 V naught, 50 divided by 12.5, 12 चौके 48, 4. That's it. What did I do? I took 12.5 common. So 12.5 into 3 is 37.5. 12.5 into 4 is 50. That's it. So from here I can get the value of V naught. Two values I will get, I guess. Let me solve it. I solved it by this method only. So 2 I am getting values are 4 volt and minus 1 volt. Minus 1 volt is possible? No. If V naught is minus 1 volt, what will happen? The MOS will be off only. If V naught is minus 1, the MOS will be off. Because VDS is negative. For transistor to turn on, what is the condition? That VDS should be greater than 0 and VGS should be greater than VT. These are the conditions, right? Two conditions are there. That this should happen. That's for sure. That this should happen. But if you are saying that, your V naught is minus 1 volt, then your VDS is becoming lesser than 0. Then your transistor will be off. But that is not possible. Why it is not possible? Let's assume my transistor is off. Let's assume my V naught is minus 1 volt and let's assume my transistor is off. What will happen then? V naught by 2R will be equals to 100 micro. What will be the value of V naught? The value of V naught will be 200 micro into R. So 200 micro is 2 to the power 4 into R value is 40, 2 to the power minus 4, 4 into. So V naught value will came out to be 8. I am assuming if my transistor is off. Now people may have the doubt that sir, it can go into cutoff as well. Why it cannot go into cutoff? That I am explaining. If my transistor is off, what will be my V naught value? V naught value came out to be 8 volt. And if V naught is 8 volt, what will be VDS? It will be 8 volt. What will be VGS? VGS will be 4 volt. And what will be VT? VT will be 1 volt. So VDS is greater than VGS minus VT. So this will go into saturation only. If you assume your transistor to be in cutoff, we get it to be in saturation. Did you understand that it cannot go into cutoff? So I will write it down. I will certainly write it down. What I will write down? Let V naught is minus 1 volt. That is equals to VDS. That means MOS goes into cutoff. And for now, let's assume that cutoff is an possibility because we haven't checked. We have not checked that cutoff cannot be one of the possibility. Here we eradicated the possibility of being in saturation region in these kind of questions. So here we eradicated those possibility. Why so? Because we have already checked that it cannot be in saturation region. But here V naught is becoming to be minus 1 volt. So there can be possibility that it can be in cutoff. There can be one of the possibility that it can be in cutoff region. So we have to check now. So check. I am writing check. We are checking. If MOS is in cutoff, यार ये पेन का क्या हो गया है? MOS is in cutoff, then what will happen? ID will become 0 ampere. Then V naught by 2R will be 100 micro. So from here V naught will be 8 volt. V naught is 8. V overdrive would be V naught by 2 minus VT. That will be 3 volt. So here V naught is greater than V overdrive. Also this is V naught and what is VGS? VGS will be 4 volt. Also VGS is greater than VT and also VDS is greater than 0 volts. By all these three conditions, MOS goes into saturation. So cannot be in cutoff. So here we checked that most cannot be in cutoff. Now we will take the second answer, that is 4 volt. Now we will take the second answer. So if V naught is 4 volt, if V naught is 4 volt, V naught is 4 volt, that means VDS will be 4 volt only, because V naught and VDS are equal only. What will be your VGS? VGS will be 4 by 2, 2 volt. What is your VT? That is 1 volt. So what will be your V overdrive? That will be 1 volt only. So here, what is the condition? That your VDS is greater than V overdrive. That means it is in saturation region only. Initially I thought it can be in linear, but it is in saturation region only. So the assumption is correct. Assumption correct. And if the assumption is correct, so V naught will be 4 volt. So this is the answer. What did they ask? They asked the value of V naught or ID, or find the bias current. So V naught will be 4 volt. What will be the bias current? ID value they are asking. ID value. So ID is 100 micro minus 12.5 micro into V naught. That will be 50 micro, because 12.5 into 4 is 50. So ID value will be 50 micro. That's it. Or after getting the V naught value or VGS value, you can find it by the expression as well. This expression, ID equals to mu n COX W by 12. So mu n COX W by 12 will be 50 micro only. 50 micro into VGS minus VT. VGS is 2, VT is 1. So from here also you will get 50 micro answer. Or by that equation also you can get, right? So very easy, well and good. I hope you have understood all the problems. And why did I take this exercise? That also you must have understood, because here my main task was to make you understand that how do you find the DC parameter, VGS, VDS, VGS minus VT, all those stuffs. How do you get to know about the region of operation? And if you know the region of operation, how to apply the current equation? Then this is how we find. And then we will bias the transistor in a particular region. So all these transistors were biased. What do you mean by biased? Giving a DC supply, that's it. Here you are giving a DC supply 6 volt to the transistor. So all these transistors were biased. So once we bias the transistor, then we will use it in amplifier. Then we will amplify the input signal. Which signal we will amplify, how we will amplify, that we will study. But why did I take this example? Why did I take this exercise? So that you could know how to bias the transistor, then how to determine the region of operation. So that's how we determine the region of operation. The same thing will be happening in BJT as well. So same thing we will study in BJT. So these kind of questions are asked in the examination. So I hope you have understood. So let's meet in the next video. Okay, thank you. Hi everyone. So till now we have seen most physics. We have seen the internal structure. We have seen the current equations. We have seen saturation region, triode region, and the current equation. We have also seen how to find the region of operation. So these kind of questions we have seen. In the previous assignment, what did we show? We had some particular configuration given, and there were some DC bias there. It could be voltage, it could be current. So there was some DC bias, and based on that we were finding the region of operation. So what do you mean by bias? Bias means simply applying some DC. It can be voltage or it can be current. So this is what we have written. The process of setting DC operating voltage or current condition to the correct level so that an AC input signal can be amplified correctly by the transistor. So what do you mean by AC input signal that can be amplified? That we will see. But the meaning of biasing is just giving a particular DC supply. It could be a voltage, it could be a current. So let's assume this is my transistor. So I am giving a particular voltage supply to it. Some VDD I am giving, and then this VDD can drive some current that I can call ID. So I am giving some voltage supply. In the previous question we could see 5 volt, 10 volt, 100 microampere current. So the some supply we are giving, that's it. Now why is it necessary to give the supply? Why cannot I run the transistor without even giving the supply? So why I needed the MOSFET? In the first lecture when I started MOSFET, I told you why I needed the MOSFET. Why I needed MOSFET? To amplify my signal. Let's assume I am applying some voltage here, 20 millivolts sin omega t. I needed to amplify it. So let's assume in output I am getting some 100 millivolts sin omega t. So this is why I needed it, so that it can amplify my input signal. One more thing I would like to tell you, here we will always amplify small signal only. We can't amplify large signal. What do I mean by small signal? Small signal means the amplitude is small. I cannot amplify large signal. Let's talk about this mic. The same example I gave you when we were studying diode circuit. So let's talk about this mic. This mic has two things. One is the DC bias, which it is getting from this laptop. Some DC voltage it is getting. That is helping for this microphone to turn on. उस DC bias से microphone turn हो जाएगा. Then there is this voice input. I am giving some voice input here, and then this voice input is being amplified. So this particular microphone is getting two inputs. One is the bias, one is the DC bias, and the other one is my voice. That is a small signal. The bias, it might be getting 2 volt, 0.8 volt, 0.5 volt. Then there is my signal. So all these signals which needs to be amplified are small signal only. It has amplitude 20 millivolt or 40 millivolt. So all those signals are small signal. It cannot happen that I can apply 2 sin omega t and then I will amplify it. No. This much of large signal cannot be there. So that's why they ask you in the question that find the small signal voltage gain. That means small signal input is applied. Some people confuse it with frequency. It has nothing to do with the frequency. The only meaning is the amplitude is small. So this is why I needed my transistor. Let's assume I apply 20 millivolt and then I get 100 millivolt sin omega t. So that was the reason why I needed my transistor. Now what if I don't even apply the DC bias? I only apply the small signal. So what was my small signal? What if I apply only small signal? There is no DC bias. I am telling you the reason why I need DC bias. So what if I don't apply any DC bias, only I apply small signal? What will happen? In this case, what is the value of VGS? Here, in this case, what is the value of VGS? VGS turns out to be 20 millivolt sin omega t. So maximum value of VGS is 20 millivolt and minimum value of VGS is minus 20 millivolt. Let's plot ID versus VGS. VT will be some 0.5 or 0.7 or 1 volt. Let's assume my VT is 1 volt. VT cannot be so small, 0.02. 20 millivolt cannot be VT. VT will be 1 volt, 0.5 volt, 0.7 volt. At least this much value will be there. Where will be this 20 millivolt? It will be somewhere here, right? Or more nearer, but somewhere here. This 20 millivolt will be in this range. Tell me, will the transistor turn on? Your VGS value is so small that transistor is not even turning on. That's why you need to give the DC bias. Are you getting this point? Transistor लैग कर रहा है यार थोड़ा सा. Transistor doesn't even turn on. Okay, let me refresh it once, then I will start the video. Yeah, so I was saying that transistor doesn't even turn on. So to turn on the transistor, we have to give that DC bias, and then on that we can superimpose or we can apply the small signal. Are you getting this point? We did the same thing in the diode circuit as well. What did we do in the diode circuit? In the diode circuit, first we turned on the diode. We had two signals here. One was DC and then the other one was, this was the DC and then we had applied some AC. So what this DC signal was doing, it was turning on the diode, and then what this AC signal was doing, if the diode is turned on, then based on the diode current, we were getting a small signal resistance, that was neta Vt upon I diode. So in the small signal AC analysis, we were replacing this diode with the small signal resistance. That's it. This is what we were doing when we were studying the diode circuit. It is again lagging. Okay. Yeah. So here also we are doing the same thing. We are applying a DC signal that will make sure that our transistor is turned on, or in whatever region we want it to operate. It can be linear region, it can be saturation region. That we will learn in the future, that my transistor is turned on. So in what region I would want it to operate, linear or saturation. So that we will learn in the further part of the video. So here my primary target is to turn on the diode, not the diode, the transistor. So my primary target is to turn on the transistor. So for that I will give a DC bias, this VGG, and then a small signal voltage. So VGS would be DC bias plus the small signal voltage, that is 20 millivolts sin omega t. Now since this is a small signal voltage, you will not have to worry whether it may turn off my transistor. What I mean to say, let's assume if it was large, let's assume the DC signal I gave is 2 volt, okay, and the signal, the AC signal that I am applying is 1.5 sin omega t, and value of Vt of my transistor is 1 volt. Then what will happen? The minimum value it can attain is minus 1.5. So 2 minus 1.5, at some value you will get your input voltage to be 0.5 volt. So your transistor may get turned off. But since this is a small signal voltage, 20 millivolt is a small signal voltage, the region of operation will not change, because there will be a very small change. There will be a very small change in VGS. What that change will be? Very small change. That will be, maximum voltage will be 2 plus 20 millivolt, that would be 2.002 or 002. 002 will be 2 millivolt only, so yeah, 02, and minimum would be 1.98. So that is very near to 2 only, 2.02 and 1.98, very near to 2 only. So your operating condition will not change. Your operating condition will be the same. If it is running in saturation, it will be in saturation only. If it is running in linear, it will be in linear only. So that's why the applied input, the applied AC signal that we want to amplify, that is small. So we can draw it like, how will my VGS look like? So my VGS will be simply a DC plus a small signal. This will be my VGS. Versus time we are drawing. So this is the DC, that is 2 volt. 2 volt I can show here. 2 volt plus 2 volt plus the AC signal. That is imposed on it. So this point will be 2 plus 20 millivolt, and this point will be 2 minus 20 millivolt. So it will not change the operating condition. Let's see it in one more graph. We will see it in the ID versus VGS graph. So this is our ID versus VGS transfer characteristic. I am assuming my VT voltage to be 1 volt. So where will be my operating condition? This is my operating condition. I am running it at 2 volt plus 20 sin omega t, 20 millivolt sin omega t. So this is my operating condition. So my operating condition will be somewhere here. Let's assume this is my operating condition. Let's assume this is 2 volt. So what this point will be? Although it will be very nearer, but to show you in the graph, I will make it far away. So this I am thinking this will be 2 plus 20 millivolt, and this will be 2 minus 20 millivolt. So I don't need to write it down. So this is 2, this point will be 2 plus 20 millivolt, and this point will be 2 minus 20 millivolt. So basically what is my signal? My signal is something like this. My signal is 2 plus 20 and 2 minus 20 and sinusoid. So my signal is something like this only. This is my signal. बन जा भाई सही से. VGS is the input. Input I am applying 2 plus 20 and 2 minus 20. That's why I showed it like this. It is my input only. And with respect to this input, what I am getting at the output? Let's assume if my input was 3 volt. So with respect to 3 volt, this was the ID I was getting. Right? If my input is 2 volt, with respect to this 2 volt, what ID I will get? with respect to this 2 volt, what idea I will get? This idea I will get. This idea I will get. If my input is 2 minus 20 millivolt, with respect to that input, what idea I will get? This idea I will get. And if my input is 2 plus 20 millivolt, what idea I will get? This idea I will get. Are you getting this point? So at 2 volt, this idea I am getting. At 2 plus 20, this is 2 plus 20, this idea I am getting. At 2 minus 20, this idea I am getting. So this kind of waveform I am getting. I can make a better waveform here. So when you apply this sinusoid input, with respect to that input, you are getting this output. Are you getting this point? So this was the case when my VGS is 2 plus sine omega 20 millivolts sine omega t. When my VGS is, I will apply two kind of VGS. First one I am applying 2 plus V in, small signal voltage. Now the second VGS I will apply is 4 plus V in. Now I am taking VGS value to be 4. So my DC bias is 4. So it could be somewhere here, could be somewhere here, and then plus minus 20, plus minus 20, minus 20 and plus 20. थोड़ा और आगे बनाना पड़ेगा. Gap should be similar, no? Gap is the similar now. This is 4 volt. Here this is 4 plus 20, here this is 4 minus 20. So this is my input. With respect to this input, what I am getting? What output I am getting? When you apply this input, this is the output you are getting. Output is very much amplified. You can see it, right? This was your input, output is very much amplified. Here this range is same, that is 40 millivolt. This is same, but here the amplification was this much. Here the amplification is this much. Here your magnitude has increased. So what did you see here? When the slope is higher, at this point this was the slope. The graph is going something like this, like this. The slope is continuously increasing. So the point where the slope is higher, you are getting more current in the output, and if there is more current, that means there will be more gain. Why so? Because this is your MOS. Let's assume this is your MOS, and this is the VGS, and then you have a ID, and this is your load RL, and let's assume you are collecting your output here. Based on your VGS, you are getting more current. If you are getting more current, that means there will be more voltage drop across RL. If the current is more, there will be more voltage drop across RL. That means the V0 value will be larger. If V0 value is larger, that means there will be more gain. That's it. If V0 value is larger, that means there will be more gain. If V0 value is low, the gain is low. So more ID, that means more gain. So when your slope is higher at the point, this point, when your slope is higher, your gain is more. So here I can write del ID by del VGS at what point? At VGS 2 is higher than del ID upon del VGS at point VGS 1. So I got to know that in this case I will get more gain. In this case I will get more gain. Here I am getting more gain. So now this parameter becomes an important parameter, that is output current divided by input voltage. Now this is an important parameter for us. So let's revise what we have studied in this lecture till now. So first we started with what do you mean by biasing, giving a DC supply. Why do we need the biasing? If we only apply the small signal voltage, what will happen? The transistor will not even turn on. So to turn on the transistor, we will apply a DC bias. Now after DC biasing, we will superimpose the small signal input voltage. If we are after superimposing the small signal input voltage, it will not affect the region of operation. Why so? Because the limit is very small, 2 plus 20, 2 minus 20, very small range it is, so it will not affect the region of operation. Now then we saw that in graph we saw that if we are giving the DC bias to be 2 volt, then the amplification we are getting is this much. If we are giving the DC supply to be 4 volt, then this much amplification we are giving. So at the higher VGS we are getting more amplification. That means when the slope is higher we will get more amplification. Now at 6 volt there will be higher slope, so we will get more amplification. So what do you think here? Now what do you think? That we should keep VGS value to be very high. What do you think? Here by seeing this graph until now, what you will think that we should keep VGS value as high as we can, because at higher VGS we will have more slope, and if there is more slope that means there will be more gain, and this is what we want. So we should keep VGS value to be very high, but this is not the case. We have to find an optimum value of VGS, not very high. What will happen if VGS value is very high? First thing, more power consumption. Power consumption will be more. If VGS is very high, that means you have to give more supply from your side. Let's assume VGS is 10 volt, so you have to give at least 10 volt from your side. So this much voltage you will give, that will eat up more power, and who knows, your chip cannot take this much of power. When you are designing chip, on chip there are transistor only, there will be these kind of MOS only, and you have to give them bias. You have to bias all those transistors. So if you bias all those transistors at too much of high voltage, let's assume at 10 voltage, then your chip may burn out. So you cannot give very high voltage. This is the first thing. The second thing is that we will study later on. When we study the amplifier, then we will study that while operating the MOSFET in an amplifier region, while operating the MOSFET as an amplifier, we have to bias the MOSFET in saturation region. What did I say? When you are operating the MOSFET as an amplifier, you have to bias the MOSFET in saturation region, not in linear region. First thing is that you are operating it as an amplifier, so it has to be turned on. It cannot be in cutoff, it has to be turned on. If it is turned on, then there are two possible regions, linear and saturation. So you do not bias it in linear, you bias it in saturation. Why so? The region we will see later on. Why do we bias in saturation region? The region we will see later on. Now the thing is, if I keep on increasing my VGS value, what will happen? If I am increasing my VGS value, what will happen? VO drive will increase. If V overdrive increases, that means VDS will be lesser than V overdrive. That it will go out of saturation. If I keep on increasing my VGS, my V overdrive will increase. If my V overdrive will increase, that means my transistor will fall out of saturation, because V overdrive is increasing and VDS is small only. So if VDS is small and V overdrive is keep on increasing, so my transistor will fall out of saturation region and I cannot operate it as an amplifier. So when you are operating the MOSFET as an amplifier, you have to make sure that the VGS value cannot be too large. First thing is the power consumption. If it is very large, there will be more power consumption. And second thing is your transistor may fall out of saturation. The region I explained, and now I will just write down the region. Okay, I will just write down why I cannot keep VGS value to be very high. We will try VGS value to be high. We will try to keep VGS value to be high, but cannot keep very high. So this parameter becomes very important. Del ID upon del VGS. We will try to get as much del ID by del VGS as much we can. We need del ID by del VGS to be very high, right? So this I will write down. At higher VGS, you get higher value of ये सही से नहीं लगा हुआ क्या, लैग तो अभी भी कर रहा है ना. Get higher value of del ID by del VGS, and that eventually gives more gain. But while
using MOS as an amplifier you cannot keep VGS value, VGS DC I am writing, VGS DC value to be very high. Like you cannot keep from 2, 4, 6, you cannot keep 6, 7, 8. That much value you cannot keep. There are two regions, right? What are the two regions? Value to be very high. What are the regions? First is the Y. First is the more power consumption. Then, and what is the second region? Transistor MOS will fall out of saturation. And why do we need to keep it in saturation? That we will study in the further part of the lecture. In the next video or next to next video, we will see. Why do we need to bias it in saturation region? So this you have understood, right? Now, this del ID upon del VGS is an important parameter, and we have given this parameter a name that is known as transconductance. So what is transconductance? That we show by GM. GM is the transconductance. So what is transconductance? The change in output current with respect to the change in input voltage. This is known as transconductance. I don't need to write the definition. I guess this is more than enough. The change in output current with respect to the change in input voltage. एंड राइटिंग एक बार चेक कर लेते हैं कैसी आ रही है. थोड़ी तो खराब आ रही है आज यार हैंड राइटिंग. ठीक है, थोड़ा लैग कर रहा है. आई होप यू पीपल आर फाइन विद दैट. सो द चेंज इन output current with respect to the change in input voltage, that is known as transconductance. And more GM, that means more current. More GM means more output current, and more output current, that means more gain. So let's consider an NMOS. This is an NMOS. So what will be the GM for this NMOS? What will be the GM? GM will be del ID upon del VGS. Make sure I am writing capital ID and capital VGS. What do you mean by that? Large signal. That means if I am saying large signal, that means I am talking about DC. Small signal means small signal AC signal. And if I am saying large signal, that means I am talking about DC only. So GM is a DC parameter. GM is a DC parameter that can be found with the expression of del ID by del VGS. Output current divided by the input voltage. That's it. So for triode region, for triode means linear region only. So for linear region and saturation region, we can find the value of GM. So for triode region, what is the value of ID? That is mu n COX W by L VGS minus VT into VDS minus VDS square by 2. What will be the expression of GM? GM expression is only one. Always there is only one expression of GM, that is output current by change in output current with respect to the change in input voltage. So del ID by del VGS. This is the GM. So GM would be del ID by del VGS. So you have to differentiate it with respect to VGS. Mu n COX W by L. Now you will go inside. VDS is a constant one. VDS is a constant value only. Why it is constant? Because we are differentiating with respect to VGS. So only VDS will come. If you differentiate it with VGS, this will be 1 and VT will be 0. So 1 minus 0 into VDS, that would be VDS only. And when you differentiate it with VDS square, it will be 0 only. So simply your GM for triode region, GM for triode region came out to be mu n COX W by L into VDS. Many times students ignore this formula because this is not oftenly used, but they can ask you 1 or 2 marks of numerical kind of question from here. That they will ask you the GM of triode region. GM of saturation region is oftenly used. We will find it again and again, but this we don't use again and again. Only once or twice we will see it. So I will take a numerical example so that you remember it actually. Okay. So you have to remember it. Sometimes they can ask you question from triode region as well. They will just simply give the mu n COX WIL value, they will give the VGS VT value, they will give the VDS value. Then they will say find the transconductance of this given configuration. Then blindly you will go for saturation region. No, first you need to check the region of operation. If you go to know that the region of operation is triode, then you have to apply this formula. The formula will change. The formula for transconductance in saturation region will be different. What that will be? Let's check that. This is transconductance for triode region. Transconductance for linear region I did not write. Okay. So in the next page I am going to write transconductance for saturation region. Transconductance for saturation region. What that will be? Simply write the expression. What is the expression of saturation region current? Mu n COX W by L VGS minus VT whole square by 2, right? Now if you, what is the expression of GM? That is del ID upon del VGS. That's it. Output current divided by input voltage. So what will be the expression of GM here? Del ID by del VGS, that would be mu n COX W by L, because this 2 will come ahead. So 2 and 2 will get cancelled, VGS minus VT. I hope you know how to take the differentiation, right? So this will be the expression of GM for saturation region, which is very important. We will use it again and again, but this also you need to remember. This also you will remember. Well and good. You will certainly remember, right? Because this is also very important one. Yeah. So this we have found. Now GM versus VGS curve, that this we are drawing for saturation region. For saturation region. Just a second, is lagging too much. Just a second. Yeah, so GM versus VGS graph we were drawing. So for saturation region we are drawing. For saturation region. So what is the expression in saturation region? Mu n COX some constant value VGS minus VT. So after VT it will start. Before VT the GM will be 0. Why so? Because current will be 0. When VGS value is lower than VT, the current will be 0. So there is no meaning of GM. It will be 0. After that, linear expression is there. But in reality, this is not the graph. In reality, the graph is different. And that we will study very in depth, but in EDC. That is important for EC guys only. This is not important even for placements. They will not ask you GM versus VGS graph. When we study EDC, I will tell you very in depth for linear region as well, for saturation region as well, how the graph goes something like this. Something like this. So we will study in depth how it goes like this, why it goes like this. So for linear region as well, for saturation region as well, we will study the in-depth concept of transconductance. Even the current expression will change. Something different will be happening. But this is not that much important for circuit analysis part. For circuit analysis part, this is just a graph I made in front of you, so that if anyone asks you what is GM versus VGS, then you can roughly make something. You can tell him those expression, because these expression will be used. But for circuit analysis part, this graph is not important. I just drew it here. When we study device physics, we will study very in depth about it. And electrical guys need not to worry that what will happen if someone asks us this, they are not going to ask you these questions, because that is in-depth analysis of device physics. So yeah, just here I drew it. No need to worry about it. Just remember these two things. GM for triode. What is GM? The change in output current with respect to the change in input voltage. What is the expression for triode region? You don't need to mug it up. You can derive it even in your brain. Okay, the current equation I know. You just need to differentiate it with respect to VGS. I never mug up this formula. I just derive it there only, because one step it will take. That's it. Del ID by del VGS, so mu n CX W by L into VDS. And what about this? That is mu n CX W by 2L W by L VGS minus VT. Now, this is one formula. I told you saturation region is important. So for saturation region, we will write two more formulas that we will derive from this formula only. This formula we have got del ID by del VGS, that is mu n CX W by L VGS minus VT, but we will derive two more formulas because that is important part. You can at any time you need to use any formula. So we will derive two more formulas. So how we will derive that? So what you can see from equation 1, let's just call this as equation 2. From equation 1, what if I do something like this? From equation 1, what do? I will take this 2 here, and one of VGS minus VT downward. There are two VGS minus VT, no? VGS minus VT into VGS minus VT. So I will bring one more VGS minus VT downward. So 2ID divided by VGS minus VT. If I do this, what I will have in the right hand side? What that will have? Mu n CUX W by L VGS minus VT. Isn't it GM only? This expression, this particular expression, isn't it GM only? Yeah. Why did I do that? So that I could make the expression of GM from here. Isn't it equal to GM only? So one more formula I got for GM. What is that? 2ID by VGS minus VT. I will recommend you to remember this formula. I will recommend remembering this formula because a lot of times we use it. 2ID upon VGS minus VT. Okay, so this is the second formula. This is also very important. One more formula we can get. Again, let's write down the expression of ID. ID expression is mu n CUX W by 2L VGS minus VT whole square. I will multiply mu n CUX W by L on the both of the side. Mu n CUX W by L on both of the side I am applying into ID. Here also I will apply mu n CUX W by L. It will be the whole square, right? Mu n CUX W by L, it will be the whole square into 1 by 2. This 2 is here. VGS minus VT whole square. I can bring this 2 here, right? So I will remove it off from here. This 2 I have removed it from here and I have brought it here. And this I will take near. So what do you get? This square, this complete expression is a square, so I can take under root on the other side. So from here, what do I get? Under root 2 into mu n CUX W by L into ID, that is equals to mu n CUX W by L VGS minus VT. And what is this expression is equals to? Mu n CUX W by L VGS minus VT. Mu n CUX W by L VGS minus VT is equals to GM. So one more formula of GM I am getting. Again I am recommending to remember it. 2 into mu n CUX W by L ID. That's it. Can you remember this? I hope you can remember these three formulas, which are very important. Why we are writing these three formulas? Because we are going to use MOSFET in saturation region for amplification, and GM is a very important parameter. So we are checking all the possible conditions. One of the expression is this, one more expression is this, and the most common expression is this. At any time you may need to use any formula, so you should be ready for that, right? What if in the question they have given only mu n Cx Wi L and id value? You have mu n Cx Wi L value and id value. From there you can find the GM expression. What if in the question you have id and VGS value only, or VT value? From there also you can find the value of GM. What if in the question you have mu n Cx Wi L value and VGS VT value? From there you can find the value of GM as well. So there are multiple ways of finding GM values. For saturation region only. For triode region, this is the formula. Only one formula is there for triode region. Well and good. Understanding this concept, let's move on to the next one. So why did we find this GM? Because higher GM means higher gain. Higher GM means del ID by del VGS is higher, that means slope is higher, that means higher gain. But we cannot keep on increasing the slope because we may fall out of saturation, or there will be more power consumption, right? So this much we have seen. After that we should start studying the biasing. Now we will see how to bias the circuit, how much bias we can apply, how to bias the circuit, like where I should give the 5-volt voltage source, where I should give the current source, that we will study. But before that I will give one more important concept and some questions we will solve. So these are the questions given in front of you. There are two questions. You have to find the transconductance. So M1 and M2 are identical. M1 and M2 are identical MOS with transconductance GM. Both are having GM transconductance. M1, M2, I did not even show. This is M1, this is M2. Both are having GM transconductance. So what do you mean by that? And what do you mean by this line, this dotted line? That means this Vin and Vin are shorted. Both of the transistors are having same input voltage. That's it. This dotted line means at gate you are having Vin, and here also at gate you are having Vin only. This is what this dotted line means. They could have shown it this way as well. They could have shown it like this. But in many questions you will find these dotted line as well. If they had shown like this, then you could have simply understood, okay, Vin is going in this transistor as well, Vin is there at M1 as well, Vin will be going to the M2 as well. But they can show it by dot as well. If they are showing by dot, what does that mean? That both of the transistor is having Vin voltage at the gate. You need to find transconductance of the overall configuration. So this is your overall configuration. That's it. So for your overall configuration, let's make it smaller. This is your overall configuration. So for your overall configuration, what is the input? Vin. What is the output current? I out. That's it. So what will be the overall GM? Overall GM. Overall transconductance. That we can say capital GM I am writing. That would be del I out upon del Vin. So this is what you need to find. That's it. This is your target. You need to find del I out by del Vin. Now GM of this transistor is given, GM of this transistor is also given. So अरे space ही नहीं छोड़ा मैंने. For transistor M1, for M1, what will be the GM? GM will be this current which is not given. Let's assume I call this I1 and this current I call I2. The current in M1 is I1, the current in M2 is I2. So what will be GM? That would be del I1 by del Vin, right? And for M2, what will be GM? Del I2 by input is the same only, del Vin. Now what is your capital GM? Capital GM is del I out by del Vin. But one thing you can see is that, what you can see? That your I out is equals to I1 plus I2. Say yes or no. I out is equals to I1 plus I2. I out is equals to I1 plus I2. This is the output current, which is the addition of these two current. And based on that, I could find the value of GM. GM is del I1 by del Vin, del I2 by del Vin. So I can simply replace this del I out with I1 plus I2. What do you get from here? del I1 by del V in plus del I2 by del V in. What is del I1 by del V in? That is GM. And what is del I2 by del V in? That is also GM. So overall GM will be twice. That's it. Here the overall GM is twice. When we connected them in parallel, the overall GM became twice. What did I do? First I found out the value of GM. That I found out. Then here also again I found out the value of GM for M2 then M1. My first target would have been to find the final expression. What do I need to find? What do I need to find? Del I out by del V in. This is what I need to find. Then I could see that in M1 transistor my GM is del I1 by del V in, and in my M2 transistor my GM is del I2 by del V in, and I out is the combined expression of I1 and I2. So I out is I1 plus I2. So basically del I1 plus I2. So del I1 by del V in plus del I2 by del V in. So GM plus GM 2GM. That's it. That's my answer. So many people confuse it with very complex analysis, like they introduce in MOSFET amplifiers and all those things. But this is not related to MOSFET amplifier. We haven't even studied MOSFET amplifiers. Still, we are able to solve these kind of problems. So it's not related to MOSFET amplifier. There is only one simple expression for transconductance. That is output current by input voltage. Change in output current by change in input voltage. Tell me the answer of this question, this particular question. What will be your overall GM? For this whole expression, this is the DC bias, right? So overall GM is del I out by del V in. Overall GM, overall transconductance. Change in output current divided by change in input voltage, that is this. This is your capital GM. Tell me what is the expression of GM1? The transconductance of M1 and M2 is GM1 and GM2 respectively. So what is GM1? What is GM1? What is that output current for transistor M1? What is the output current for transistor M1? That is del I out. What is the input voltage for transistor M1? That is del V. Isn't it the same as capital GM? That's your answer. That's it. What do you need to find? The overall transconductance. No matter how many transistors you add up, you can add up M3, M4, M5, M6, M7, but the input is applied to M1 only. And the same current will be flowing in all the transistors because they are in series. Let's assume I keep on adding up transistor. These all are transistor. I keep on adding up M3, M4, M2, M4, M5. But the final input is applied to this transistor only. And the same current is flowing. So overall transistor would be output current divided by input voltage. And the same transconductance will be there for M1 as well. Why so? Because it has the same output current and it has the same input. So your GM is small GM1 only. That's it. So this is your answer. Did you understand it? No need to confuse yourself when you see these kind of questions. Just write down the simple expression that I have taught. What I have taught will be more than enough for you in the examination, in any interview. Just you need to believe in yourself. You just need to write the expression. What is the expression of transconductance? Change in output current with respect to the change in input voltage. Del I out by del V. And what is the transconductance for M1? M1 has the same transconductance, that is output current is I out only, input voltage is V in only. So it would be GM1 only. That's it. So these two questions we have solved. Now we will see one more important parameter. This is not the concept, it is a parameter, that is output resistance. What is an output resistance? If I am asking you find output resistance, what do you do? I give you a network and I am asking you find output resistance. So here what you will do, you will apply a voltage and get the current out of it. That's it, right? In case of MOSFET, what is our output? Input is VGS, output is VDS. So from VDS, how much current is coming? That will give the resistance. That we call output resistance. So from VDS, how much ID is coming? So dial VDS by dial ID will give us resistance. And this is the characteristics that we have studied. For linear, it will rise like this, and this one is for saturation. Saturation. Right? Saturation. Linear and saturation. And saturation, we studied about two things. One is the ideal, when your channel length parameter lambda is 0, and one is practical, when your lambda is infinity. We also found out the value of RDS when we studied MOS physics. When we studied the MOS physics, do you remember we found out the value of RDS? When we were studying channel length modulation, we found out the value of RDS in saturation region. What was the expression, if you remember? That was 1 upon lambda ID for practical case, and for ideal case, R naught was infinity. Do you remember it? For practical case, the expression was 1 upon lambda ID. If you don't remember, I will make you recall. So this was the ID saturation expression, right? This is the expression of ID saturation. So here, if I do 1 upon del ID by del VDS, what will happen? This is a constant expression, and 1 plus lambda VDS. So you are just differentiating it with respect to VDS. So what will remember? Only lambda will remember. Are you able to understand? So lambda will be there. So what will be your expression? Your expression of RDS would be 1 upon lambda ID saturation, but for ideal case. Ideal case, right? So this we have already derived when we were studying MOS physics. You can check out there. Very simple derivation is there. So this is the practical one. Practical one. What is the RDS for practical? That is 1 upon lambda ID sat ideal. So lambda will be value will be given to you in the question. Then you can find out the value of RDS. How will you find out? Because you have the value of lambda, you can find the ID saturation. But in ideal case, what is the expression of this? That is mu n Cux W by L. This will not be there. This is eradicated. I am asking you to write the ID saturation in the ideal case. In ideal case, lambda will be 0. If you just differentiate it, what will happen? If you just differentiate it, del ID by del VDS, what you will get? Mu n Cux W by L VGS minus VT square into lambda. That's it. Now what is this? ID saturation in ideal case. So that will be lambda into ID saturation in ideal case. So just the inverse we have to take, because RDS is del VDS by del ID. So inverse we have to take. So after taking the inverse, this is what we are getting. And in case of ideal case, what do you get? You get it to be infinity, right? In case of ideal case, you get RDS to be infinity. Why it is infinity? Because if you differentiate this expression with respect to VDS, what will be the answer? 0. Del ID by del VDS will be 0, because there is no expression of VDS for the ideal case. This is for ideal case. Ideal case. In the ideal case, there is no VDS involved. If there is no VDS involved, that means the expression will be 0 only. And if it is 0, the RDS will be infinity. So this is the story for saturation region. Practically it is 1 upon lambda ID, and ideally it is infinity. So MOS in saturation region. So MOS in saturation region, if you are seeing from this terminal, so MOS in saturation region can be replaced with the simple current source. Simple current source, but with the output resistance of RDS. With the output resistance of RDS that has a value of 1 upon lambda ID sat, but ideal case. Current source, constant current source. This is for practical scenario. And what is the scene for ideal scenario? It will simply be replaced with the current source only. This when we are seeing from drain to source terminal. If you are seeing from drain to source terminal, then only you can replace it with the current source. It's not that if I am seeing from here, I will replace it with the current source. No. From here it is not a current source. From output it is a current source. From output it acts like the current source, not from the input side. Well and good. So from output it is acting like a current source. So this is drain to source. Here this is also drain to source, and this is current source. Now people say that it is a constant current source. Yeah, this will be a constant current source, but only when VGS is constant. In some question your VGS will be varying. Let's assume my MOSFET is in saturation region. I am telling one of the statement, that is my MOSFET is in saturation region, that I am saying, but my VGS is varying. My VGS is varying, still the MOSFET is in saturation region. So what will happen to my current source? The current source value will also vary, right? The ID versus VGS plot we make. This is our ID versus VGS plot, right? ID versus VDS, sorry. ID versus VDS. So in this region we are working. So here we are saying that it is acting as a current source, but for a particular VGS only. What if my VGS is varying? What if my VGS is VGS2? So the value of current will be changed. Here the value of current is this. Here the value of current is this. So you can't say this will be a constant current source. This will be a current source depending on the value of VGS. That's it. In the saturation region, you can replace the MOSFET with the current source and the output resistance, but the current source will have a varying value with respect to VGS. If the VGS is constant, then the current source will be constant. Did you get this statement or not? So you can't directly say this statement is wrong, that in saturation region MOSFET is replaced with the constant current source. No, MOSFET is replaced with the constant current source only when VGS is constant. If the VGS is varying, even the current source will be varying. So in the saturation region, you can only replace the MOSFET with the current source. Now the value of current source depends on VGS. So I will be a function of VGS. This is what I will write. This I will be a function of VGS. This I will be a function of VGS. Okay, so saying that in MOSFET region, in saturation region, MOSFET is replaced with a constant current source, that is wrong. MOSFET is replaced with a current source. The value of that current source depends on the VGS value. That's it. Well and good. Now let's do the same thing for triode region. But triode region is very interesting. Why it is interesting? Let's check that out. So in triode region, actually there are two regions. One is the deep triode, other one is the sublinear. Let's check that out in the next page. This is nothing written, it is just the expression of triode region current is there. So let's study that triode region more deeply. This is your ID versus VDS plot. So when you draw the curve, there is always a curvature there. It's not that it rises like this and then this. There is a curvature. And what I was saying, that in linear region the current increases linearly. Here I can see that the current increases linearly. But is it happening by this expression? I am saying ID versus VDS is a linear expression. But is that so? See the current expression. In the current expression, there is a term of VDS square by 2. There is a term of VDS square by 2. So is that linear? No, this is not linear, because there is a term of VDS square by 2. But when the value of VDS is low, that means in this particular region, When the value of VDS is low, we can assume this expression going towards 0. Are you getting this point? When the value of VDS is low, we can assume VDS square by 2 going towards 0, and that happens in deep triode region. So we call this region as deep triode region. Deep triode region, and this region is known as this one, sublinear. This is not completely linear, this is sublinear. Here VDS square will be coming in action. Are you getting this point? Here VDS. So in deep triode region, what do you see? Del ID by del VDS is a straight line. For a resistance, if I plot V versus I curve, how will the curve look like? Voltage versus current. How will the curve look like? A straight line only. If voltage is increasing, that means current will also increase. So for a resistor, what happens? VI curve is linear. VI curve is linear. In MOSFET characteristic, what do we see? In deep triode region, there is a linear relation between output current and output voltage. So the expression is linear only. So in deep triode region, you can replace the MOSFET with the resistor from output terminal. And what will be the value of that resistor? That we can find by simple expression. So what will be your RDS? And we call it R on actually. We call it R on. The expression that we write, that we call R on, not RDS. RDS expression is given for saturation region only. So for linear region, we generally call it R on. So R on will be del VDS by del ID. That would be 1 by del VDS by, 1 by del ID by del VDS. Del VDS. I will put on the charger. Yeah. So R on is 1 by del ID upon del VDS. And for deep triode region, for deep triode region, what is the scene? VDS is very small. By the way, what do you mean by very small? So typically VDS should be lesser than 2 VGS minus VT. That is the typical value. ओके, ये तो कुछ गड़बड़ लिख दिया मैंने लगता है. 2 VGS मैंने VGS माइनस VT मान लो 1 वोल्ट है तो VG ना this should not be the scene. It should be VGS minus VT by 2, right? VDS should be lesser than VGS minus VT by 2, because if VGS minus VT is 2 volt, yeah. So typically this is the scene. Typically, this is not a hard and fast rule. It is not any hard and fast rule. Okay, don't remember it. Okay, if it is lesser than that, you just need to compare. If you find that VDS value is typically small, this expression can go to 0, then you can take this as 0. Let's assume if VDS value is 0.1 only. If it is 0.1, what will be the square of that? 0.01. 0.01 by 2. That will be very low. That will be very low. So this can go to 0. So typically your VDS can go to 0. If VDS value is very small, so your VDS can typically go to nearly go to 0. So what will be the expression of ID? Expression of ID will be mu n Ux W by L VGS minus VT into VDS to VDS. So what will be del ID by del VDS? That would be mu n Cux W by L VGS minus VT. And what will be your R on? R on is typically 1 upon del ID by del VDS. That would be 1 upon mu n Cux W by L VGS minus VT. VGS minus VT. That's it. Again, you don't need to mug up this formula. You can derive it anytime. So there are many formulas in this particular video. This R1 formula is there. Then one more formula we find. For RDS, these formulas are there, right? But you don't need to mug up anything. You just need to know the expression that okay, what is output resistance? Del VDS by del ID. You know the expression of ID. You can find it out in one expression only, or even in the brain you can think about it. Okay, del ID by del VDS. For saturation, I need to find in saturation region. It doesn't even depend on VDS. It will be infinity. If this is not the if this is not ideal case, okay, it is practical case, then there is channel length modulation. So lambda factor will be coming 1 upon lambda ID set. That's it. For this deep triode region, okay, deep triode region, VDS square will be going towards 0. So only mu n CX WIL VGS minus VT will be remaining. So 1 upon mu n CX WIL VGS minus VT will be my expression. For GM also I don't need to mug up the formula. For triode region I can find, okay, for triode region, what is the expression of my GM? Del ID by del VGS. So expression will be mu n CX WIL into VDS. That's it. For triode, deep triode, for every region. Here there is no meaning of triode or deep triode. For every region, this will be the formula only. Because here the differentiation is made with respect to VGS. So this expression and this expression are itself going towards 0 only. This one is going towards 1 and this one is going towards 0. So there is no meaning of triode or deep triode. The formula of GM will be the same for both of the region. And then when we talk about transconductance for saturation region, this is very important parameter. So for that we have to remember two formulas. This we can derive very quickly, mu n CX WIL VGS minus VT. Then the other one is 2ID upon VGS minus VT. This I will keep in mind, 2ID upon VGS minus VT. And the other one is root 2 into mu n CX WIL into ID. That's it. So these formulas I will remember, root 2 into mu n CX WIL ID. So these three formulas I will remember, and then I found out how to find the expression of GM just by the simple formula we have to go. Nothing, no concept of MOSFET amplifier used. Simple formula is there. Then we find out the output resistance. Okay, so this was the summary of this lecture. And one more thing I need to show, that is how will I show the MOSFET in saturation region. Like here I showed the MOSFET in saturation region, so here I will show the MOSFET in triode region. So MOS in triode region. So it will be replaced with the resistance. Gate, source, drain. So it will be replaced from drain to source side. It will be replaced with the resistance of R1. That's it. This is drain and this is source. Okay, in triode region. Okay, not in triode region, in deep triode region. MOSFET in deep triode region. In deep triode region, it will be replaced with R1. The form expression is here, 1 upon mu n CX WIL VGS minus VT. I hope you have understood the complete lecture. By using all these things, whatever that we have studied in MOSFET till now, we have seen the MOS physics, then we saw some question. Now we have seen the important parameter. Like first we saw why do we need to bias, like understood why do we need to bias, so that the transistor turns on, then we can amplify it. When we saw the biasing, what did we saw there? We see that del ID by del VGS is a very important parameter. Higher the slope, more the gain. So at high value of VGS, you get higher slope. So then I found out the expression of del ID by del VGS for both of the region, for saturation and triode, and then we saw the output resistance. Output resistance is also an important parameter. When we study amplifier, it will be used there. So output resistance is also an important parameter. So we also studied about the output resistance. So that expression also we found out. Well and good, very easy. So let's move on to the next lecture. In the next lecture, we will see very important assignment. These kind of questions are not asked in GATE till now, but they can be, those questions can be asked any day. So in the next lecture, we will solve those assignments. Okay, thank you.
Yeah, hi guys. So you have watched all the videos, right? All the content you have watched, whatever the topic that has been mentioned, everything is clear. Now what we are going to see? We are going to see the known idealities in MOSFET. okay, which are not discussed in analog videos. So this was a particular video which was taken from analog. Now we are going to study some different topics which are not discussed in analog videos. So those topics would be, first we will study body effect. These are basically like the non-idealities of MOSFET. So first we will study body effect, then we will study something called sub-threshold region. Like I have said that if your VGS is less than VT, then there will not be any current, but there will be some current. So why there will be some current, what kind of current would be there, so that we will see. And then we will see mobility degradation. Like if you keep very high VGS, then what will happen? High VGS means more and more inversion charge. If more and more inversion charge is there, that means scattering would be more. If scattering is more, that means your mobility will be decreased. So till this point we used to say that mu n Cux W by L, this is constant, but at higher VGS this guy will decrease, right? So this phenomena also we need to understand. So 3 points we will see, and with that our video will be completed, okay, and our complete MOSFET will also be completed. So yeah, so this video is completed. Let's move to the next one. Yeah, thank you very much.